In the late 1970s, two small machines left Earth with a mission. They were sent to wander outward, to see worlds no human eyes had ever seen, and to send back their stories across billions of miles of empty space. Few expected them to last beyond their first encounters, yet decades later, both are still alive, still traveling, and still changing what we know about the universe. What began as a mission to study the outer planets turned into something far greater. Voyager 1 and 2 showed us volcanic moons that erupt into space, hidden oceans beneath frozen crusts, violent storms larger than Earth itself, and the boundary where the sun's power finally gives way to the galaxy beyond. Each discovery was unexpected, a reminder that the universe is far stranger than we had ever imagined. The 1970s moment, why NASA dreamed of reaching the outer planets. In the early 1970s, NASA stood at a crossroads. The Apollo program had achieved what many once thought impossible, landing humans on the moon and returning them safely to Earth. For a brief moment, it felt as if there were no limits to what space exploration could achieve. Yet, once the moon landings became routine, a question began to echo through the halls of NASA and the wider scientific community. What comes next? The thrill of Apollo was fading, public interest was drifting, and Congress was cutting budgets. NASA needed a new challenge, something ambitious enough to capture the imagination of the world once more, but also practical enough to justify the resources required. That challenge emerged in the form of the outer planets. At that time, Jupiter, Saturn, Uranus, and Neptune were mysterious giants that had only ever been observed from Earth's telescopes. Through those distant lenses, they appeared as blurry disks with faint details. Scientists longed to see them up close, to uncover their secrets, to understand their atmospheres, their magnetic fields, and whether they had moons of interest. The moon had been conquered, but the solar system was still full of mysteries waiting to be revealed. To many within NASA, the next logical step was to send robotic explorers far beyond the orbit of Mars, into the cold and distant reaches where the gas and ice giants resided. The timing for such a mission was particularly compelling. Astronomers had realized that during the late 1970s, a rare alignment of the outer planets would take place. This arrangement, occurring only once every 176 years, meant that a single spacecraft could use the gravity of one planet to slingshot itself toward the next. By carefully plotting a trajectory, a probe launched in the late 1970s could visit Jupiter, then use its gravity to speed towards Saturn, and from there onto Uranus and Neptune. This Grand Tour, as it was called, was an unprecedented opportunity. Normally, reaching the outermost planets would require immense amounts of fuel, time, and resources. But with the planetary alignment, the journey became not only possible but also practical within the technological limits of the time. The idea sparked a wave of excitement among scientists and engineers. Here was a chance to extend human knowledge of the solar system in ways never before imagined. The planets beyond Mars were largely unknown worlds with only faint hints of their true nature. Were Saturn's rings made of solid bands or countless icy fragments? Did Jupiter's giant red spot churn like a storm or sit like a scar in the atmosphere? Could Uranus and Neptune, almost invisible to the naked eye, hold surprises that might reshape our understanding of how planets form? Every question carried with it the promise of a discovery that could rewrite textbooks. But there was another reason NASA dreamed of the outer planets. After Apollo, spaceflight risked becoming a story of limits rather than possibilities. The United States had won the race to the moon, but without a new frontier, there was the danger that space exploration would stall. The outer planets represented the next chapter, a way to show that humanity's reach was not confined to its immediate neighborhood. Sending probes to Jupiter and beyond would prove that the technology developed during Apollo could be adapted to even greater challenges. Of course, the dream was not without obstacles. Budget cuts in the early 1970s were severe. The Apollo program had drained national resources, and the Vietnam War had shifted priorities away from grand scientific projects. Many inside NASA feared that the idea of a grand tour would be dismissed as too ambitious, too costly, and too long-term to be realistic. After all, a spacecraft launched in the 1970s might still be operating decades later, long after the original team had moved on. Convincing policymakers to fund such a mission would not be easy. Yet the scientific case was compelling. The outer planets were keys to understanding the solar system. The gas giants contained most of the solar system's planetary mass, their gravitational pull shaping the orbits of countless moons, comets, and asteroids. Their atmospheres were ideal for studying physics and chemistry under extreme conditions. Their moons hinted at complex geology and perhaps even the ingredients necessary for life. Exploring them was not a luxury. It was essential for answering fundamental questions about how planets form, how they evolve, and where Earth fits into that larger picture. It was within this context that the Voyager program was born. Unlike Apollo, Voyager would not carry astronauts but rather robotic emissaries, packed with instruments and cameras designed to withstand the deep cold and high radiation of the outer solar system. These spacecraft would not just fly past the planets. They would observe, measure, and transmit their findings back to Earth, providing humanity with its first close-up views of worlds that had only ever been specks of light in the sky. The decision to pursue Voyager represented a turning point for NASA, a shift from human exploration of nearby worlds to robotic exploration of distant ones. What made the idea so powerful was that it combined practicality with vision. On the one hand, the planetary alignment gave the mission a narrow launch window that could not be ignored. On the other, the possibility of exploring 4 giant planets in a single mission carried a symbolic weight. It spoke to humanity's hunger to go further, to push boundaries, to see what lay beyond the horizon. Just as Apollo had been about more than landing on the moon, Voyager was about more than sending machines into space. It was about proving that exploration was not a momentary achievement, but an ongoing endeavor. In that decade, when many feared the space age was fading, the seeds of Voyager were planted. The outer planets, distant and mysterious, stood as symbols of the next great challenge. And in daring to imagine reaching them, NASA ensured that exploration would remain a defining part of our story. The hidden opportunity, the rare planetary alignment. The outer planets circle the Sun on paths that take many years to complete. Jupiter takes almost 12 years for a single orbit, Saturn nearly 30, Uranus 84, and Neptune 165. Because of these long cycles, their positions rarely line up in a way that makes visiting more than one of them practical. But in the early 1970s, astronomers realized that for a brief window, all 4 outer planets would be arranged in such a way that a spacecraft could swing past one and use its gravity to propel itself to the next. Normally, sending a spacecraft to Neptune or Uranus would require enormous amounts of fuel. Rockets could only carry so much, and the distances involved stretched the limits of what was technically possible. But with the planets positioned just right, a spacecraft could use a gravity assist or slingshot maneuver. This technique had been demonstrated before on smaller missions, but never on such a grand scale. NASA understood the stakes. If they missed this window, the next chance would not come for another 176 years. By then, the scientists, engineers, and decision-makers alive in the 1970s would be long gone. Entire generations would have to wait before the planets aligned again. The pressure to act was immense. In a period when budgets were shrinking and doubts were growing about the future of space exploration, the alignment stood as a reminder that some opportunities, once lost, could never be regained. When a spacecraft approaches a planet, it falls into the planet's gravity well, gaining speed as it draws closer. If the trajectory is plotted just right, the spacecraft swings around the planet and emerges with a new course and a higher velocity relative to the Sun. It's as if the planet lends the spacecraft some of its orbital energy, while the planet itself slows down by a tiny, almost unmeasurable amount. The effect is powerful. With Jupiter's immense gravity, a spacecraft could more than double its speed, allowing it to reach distances that would otherwise take centuries with traditional propulsion. Engineers began sketching designs for spacecraft that could survive the long journey, withstand the harsh radiation around Jupiter, and keep functioning in the icy darkness beyond Saturn. The challenge was daunting, but the scientific reward was too great to ignore. Every delay risked missing the narrow launch window, and once the planets drifted out of alignment, there would be no second chance. This urgency pushed NASA to focus its efforts. Voyager was not just another mission on a long list. It was the mission. It had to succeed. The thought that within a decade a spacecraft could fly past them and send back photographs was almost beyond belief. And beyond the pictures, there were the instruments, spectrometers, magnetometers, particle detectors, that could measure atmospheric composition, magnetic fields, and radiation levels. Voyager would not just show us what the planets looked like, it would reveal how they worked. There were, of course, doubts. Some argued that a scaled-down mission to just Jupiter and Saturn would be safer and cheaper, avoiding the risks of stretching technology to its limits. Others worried that designing a probe to last long enough to reach Neptune was unrealistic. The spacecraft would need to operate for more than a decade, surviving deep space radiation, hardware failures, and the immense cold of the outer solar system. Yet the alignment made the gamble worth taking. The chance to see all 4 planets in one sweep was so rare that it overrode hesitation. Even if Voyager failed before reaching the farthest worlds, the knowledge gained along the way would still be unprecedented. As plans solidified, the alignment gave the mission an almost poetic frame. The solar system itself had lined up in a pattern that human technology could exploit, but only if human will and ingenuity rose to meet it. That sense of urgency, of rarity, of a once-in-a-century chance infused every stage of Voyager's design. From the earliest trajectory calculations to the final assembly of instruments, every decision was shaped by the knowledge that time was running out, that the planets would not wait. Engineering for the unknown. When NASA committed to Voyager, they were committing to sending spacecraft farther than any machine had gone. This raised a central problem. How do you build a spacecraft that will not just reach Jupiter and Saturn, but survive the unknown challenges beyond? It wasn't enough to design for a simple flyby. Voyager had to endure conditions that no spacecraft had ever faced, and do it without the safety net of constant repairs or updates. Once it left Earth, it would be on its own. The engineers who built Voyager knew they couldn't predict every danger. They didn't fully understand the radiation environment near Jupiter, which would prove to be one of the harshest in the solar system. They didn't know what kind of dust or debris might exist around Saturn's rings, or whether Uranus and Neptune had surprises of their own. So they had to imagine a spacecraft that could take punishment, adapt when needed, and keep going even if parts of it failed. This led to a philosophy of redundancy, backup systems for nearly everything. If one computer glitched, another could take over. If a transmitter failed, there was a second one ready to broadcast. The spacecraft was built not as a fragile experiment, but as a durable traveler, prepared for a mission that might push it far beyond its official goals. One of the most critical challenges was power. Solar panels, the standard source of energy for spacecraft closer to the Sun, were useless in the outer solar system. Jupiter alone is 5 times farther from the Sun than Earth. And by the time a probe reached Saturn, sunlight would be less than 1% of what it is at Earth's distance. Beyond Saturn, the Sun would be no brighter than a faint star. Voyager needed a power source that would last not just years, but decades, and function in near darkness. The solution was radioisotope thermoelectric generators, or RTGs. These devices used the heat from decaying plutonium to generate electricity. It was a simple, steady, and reliable power source, one that required no moving parts and could keep producing energy long after solar panels would have gone dark. The RTGs became Voyager's beating heart, still delivering power more than 4 decades after launch. The spacecraft's design also reflected the dangers of radiation. Jupiter, with its immense magnetic field, creates a radiation environment harsher than anything found near Earth. Electronics exposed to that kind of bombardment would quickly fail. To survive, Voyager's instruments and circuits were shielded, wrapped in protective layers to guard against the high-energy particles that would slam into them during close approaches. Without such shielding, Voyager's mission might have ended before it even left the Jovian system. Communication presented another daunting problem. Even at Jupiter's distance, signals from Earth took nearly an hour to arrive. By the time Voyager reached Neptune, that delay stretched to more than 4 hours. Commands couldn't be given in real time. The spacecraft had to be able to make decisions on its own, to switch to backup systems if something went wrong, to enter safe modes when it detected trouble, and to wait for further instructions. This required a level of autonomy uncommon in spacecraft of the time. The software and hardware had to work together in ways that allowed flexibility, because once Voyager was millions of miles away, a single malfunction could mean silence forever. Its central bus was a 10-sided box that housed computers, instruments, and controllers. Extending from it were long booms holding magnetometers, so that the instruments could measure magnetic fields without interference from the spacecraft itself. A massive high-gain antenna, nearly 12 feet across, pointed back toward Earth, the lifeline through which all data would flow. Every detail of the design spoke to longevity: thick cables, robust joints, components that could handle extremes of temperature, from the blazing heat of launch to the freezing void beyond Neptune. The mission planners gave Voyager flexibility. The instruments were versatile, able to collect data in multiple ways. The cameras could adjust exposure for wildly different lighting conditions. The computers, though primitive by today's standards, could be reprogrammed in flight to adapt to new situations. This ability to rewrite software from Earth kept Voyager relevant as it moved from one planet to the next, facing environments no one had predicted in detail. Voyager was, in many respects, overbuilt. For a mission whose minimum goal was to reach Jupiter and Saturn, it was designed with enough durability to keep going far beyond. At the time, this seemed like a cautious hedge, but in hindsight, it was visionary. Because of its robustness, Voyager did not die after Saturn, as some missions might have. It kept going, through Uranus and Neptune, and eventually into interstellar space. What might have been a 4-year mission became a journey lasting decades. The design choices extended even to the scientific instruments. Voyager carried cameras, spectrometers, detectors, and sensors for nearly every kind of measurement imaginable. Each instrument was built not only to perform a specific task, but also to provide overlapping information, so that if one failed, another might still supply critical data. This redundancy mirrored the spacecraft's overall philosophy: prepare for the worst, but build with hope for the best. The result was a machine unlike any that had flown before. Where earlier spacecraft had been designed for short bursts of exploration, Voyager was a spacefarer built to survive the unknown. It carried within it the lessons of past missions and the foresight of engineers who understood that space is unpredictable, that the only way to succeed was to prepare for the unexpected. Why Voyager 1 and 2 took different routes? The two Voyager probes were always destined to take different paths, even though they were built together, tested together, and launched within a few weeks of one another. Their twin design was meant to ensure reliability, yet the missions were carefully plotted so that each craft would carry out a different role. In this way, they complemented one another, rather than simply duplicating efforts. Voyager 1 was placed on a trajectory that emphasized speed and efficiency. Its job was to gather close-up data from Jupiter and Saturn, then move on quickly. After it completed its Saturn encounter, a carefully chosen gravity assist from the giant planet flung it sharply upward, out of the plane of the solar system, toward interstellar space. This meant it would never get the chance to visit Uranus or Neptune, but it would carry humanity's instruments faster than any object before it toward the outer reaches of the solar system. Voyager 2, on the other hand, was placed on a more meandering route. It traveled more slowly, deliberately timed to reach Uranus in 1986, and Neptune in 1989, after completing its own tours of Jupiter and Saturn. In this sense, the two spacecraft split the responsibilities of planetary exploration. Voyager 1 gave us a detailed look at the first two giants, while Voyager 2 gave us our only close-up view of the ice giants Uranus and Neptune. The logic behind this division of labor was deeply practical. At the time of planning, NASA could not be certain both spacecraft would survive long enough to complete their journeys. Space is an unforgiving place. By choosing different paths, scientists increased the odds that at least one of the spacecraft would fulfill the key mission goals. If Voyager 1 had failed at Saturn, Voyager 2's trajectory could still have been altered to complete the rest of the grand tour. This insurance strategy meant that one way or another, the outer planets would finally reveal their secrets to us. Voyager 1's encounters set the stage. Its close pass by Jupiter in 1979 revealed the planet as more dynamic and violent than telescopes had ever suggested. Its powerful cameras sent back astonishing pictures of swirling cloud bands, giant storms, and the volcanic eruptions of Io, Jupiter's restless moon. Voyager 1 then sped onward to Saturn, where it uncovered the complex structure of the planet's rings and studied its largest moon, Titan. It was Titan that ultimately sealed Voyager 1's path. Scientists knew this haze-covered moon was a high-priority target, and sending Voyager 1 on a trajectory to fly close enough to study it required sacrificing any chance of visiting Uranus or Neptune. But the trade-off was considered worthwhile, because Titan's thick atmosphere made it one of the most Earth-like bodies in the solar system. Meanwhile, Voyager 2 took its time. When it arrived at Jupiter a few months after Voyager 1, it carried a fresh set of eyes, confirming and extending the discoveries of its sibling. It too studied Jupiter's atmosphere, magnetosphere, and moons, capturing additional detail that Voyager 1's faster pass had not. Then, in 1981, it reached Saturn. Its instruments studied the planet and its moons once again, but with slightly different geometry and timing. Where Voyager 1 had passed above Saturn, Voyager 2 passed below, offering different perspectives. These differences were planned, giving scientists a stereoscopic understanding of Saturn's complex system. From there, Voyager 2 pressed onward into uncharted territory. In 1986, it became the first, and still only, spacecraft to visit Uranus. This distant pale blue world turned out to be unlike any other planet we had seen. Its rotation axis was tilted so far over that it appeared to roll around the Sun on its side. Its rings and moons were strange and unexpected, and Voyager 2's cameras revealed features no one had even imagined. The spacecraft continued, and 3 years later, it reached Neptune, the last planet in the solar system to be visited by a spacecraft. There, Voyager 2 discovered high-speed winds, dark storms, and a surprisingly active atmosphere. It also revealed Neptune's largest moon, Triton, to be a world of frozen nitrogen geysers and young surfaces, suggesting ongoing activity despite its distance from the Sun. The choice to split the Voyager's trajectories has shaped our understanding of the solar system ever since. Without Voyager 1's Titan flyby, we would not have had the early data that inspired later missions like Cassini-Huygens, which ultimately landed a probe on Titan's surface in 2005. Without Voyager 2's extended journey, we would know Uranus and Neptune only as faint dots through telescopes. Together, the probes painted a complete portrait of the outer planets, showing them not as static spheres, but as dynamic, diverse worlds with unique properties. The technical differences between the paths also meant that the two spacecraft experienced different fates once their planetary missions ended. Voyager 1, traveling at a greater speed and in a trajectory directed out of the ecliptic plane, crossed into interstellar space in 2012, becoming the most distant human-made object. Voyager 2, on its slower, lower path, followed suit in 2018, entering interstellar space from a different direction. These separate exits have given scientists rare and valuable opportunities to compare conditions at two different points of the solar system's boundary. By sending two spacecraft on different courses, NASA spread its bets. The result was a scientific triumph that exceeded even the most optimistic expectations. In a way, Voyager 1 and Voyager 2 are like two explorers who set out from the same shore, carrying the same tools, but deliberately take different routes into unknown territory. Each brings back stories and treasures that the other could not have found alone. Together, their paths create a fuller map of the outer system, a record that will guide our understanding for generations to come. Voyager at Jupiter, discovering worlds within a world. When Voyager reached Jupiter, it was as if a curtain had been pulled back on a stage that had only ever been glimpsed from the audience seats. For centuries, Jupiter had been seen only through the blur of telescopes. Even the best Earth-based observatories could offer little more than hints of its banded atmosphere and the fuzzy light of its largest moons. But in 1979, Voyager began sending back images that were not distant blurs, but close-up portraits. The spacecraft's cameras revealed the immense scale of the planet in a way that words could scarcely capture. The famous Great Red Spot, long observed through telescopes as a reddish oval, was revealed to be a storm larger than Earth itself, churning for centuries in the planet's turbulent atmosphere. Surrounding it were countless other storms, some stretching thousands of miles across, colliding, merging and breaking apart in patterns that looked alive. Voyager's images showed Jupiter's atmosphere as a living canvas of motion, with swirling clouds, spirals of ammonia ice, and alternating belts of color that hinted at powerful winds moving faster than anything on Earth. The data confirmed Jupiter was more than 1,300 times the volume of Earth. Its gravity dominated the region around it, shaping the paths of asteroids and comets and holding dozens of moons in orbit. But Voyager revealed that Jupiter was not just a planet, it was the anchor of its own miniature system. The four largest moons, Io, Europa, Ganymede and Callisto, were each worlds in their own right. With the spacecraft's cameras, they suddenly became landscapes with mountains, valleys, oceans of ice and volcanic fire. Io was the first to shock scientists. Voyager's instruments detected odd plumes rising above its surface, and closer inspection revealed something astonishing: active volcanoes. No one had expected to see ongoing volcanic activity anywhere beyond Earth. Yet Io was covered in erupting volcanoes, spewing sulfur and reshaping the surface in real time. The discovery completely overturned the assumption that small worlds far from the Sun would be geologically dead. Europa offered a different kind of mystery. Voyager showed its surface as a bright, smooth sheet of ice, crisscrossed with long, dark lines. Unlike cratered moons, Europa looked young, as though its surface had been resurfaced recently. The patterns suggested cracks in the ice, hinting at something extraordinary beneath. A hidden ocean of liquid water. The idea that a moon orbiting Jupiter might hold an ocean, kept warm by tidal heating, suggested the possibility of environments that could support life. What was once thought to be a frozen, airless rock was suddenly a place of enormous scientific interest. Then came Ganymede, which Voyager revealed as the largest moon in the solar system, even bigger than Mercury. Its surface showed a mix of ancient cratered terrain and younger regions of grooved patterns, suggesting internal processes had reshaped the crust. Callisto, by contrast, appeared as an ancient and battered world, its heavily cratered surface telling the story of billions of years of impacts. Each moon was different, each a world shaped by unique forces. The idea of Jupiter as a single planet faded. It was now clear that the Jupiter system was a kind of solar system in miniature. Instruments measured Jupiter's magnetic field and found it to be unimaginably strong, more than 10 times the strength of Earth's. The magnetosphere was enormous, stretching millions of miles into space, sweeping up charged particles, and creating radiation belts so intense they could fry unprotected electronics. The spacecraft had to endure this environment, and the data it returned revealed Jupiter's magnetic influence as a force that extended far beyond its atmosphere, shaping its moons and interacting with the solar wind. This magnetosphere was not just a planetary feature, it was an entire environment with trapped radiation, auroras, and invisible storms. Even Jupiter's rings were revealed. While Saturn's rings were famous, no one had been certain whether Jupiter had any. Voyager showed a faint, thin ring system circling the giant planet, invisible from Earth, but unmistakable in the images sent back. Voyager gave the public something it had never seen before: clear, detailed images of alien worlds. For the first time, people could look at the face of Io, see the cracked ice of Europa, or gaze at the swirling storms of Jupiter in colors and detail that no telescope could provide. These pictures brought the outer planets into the human imagination in a way words never could. They transformed Jupiter from a distant dot of light into a vast, complex system of worlds, each one strange, beautiful, and alive with forces no one had expected. Io's fury, volcanoes where none were expected. Voyager 1's images of Io showed a strange, colorful surface, nothing like the gray or brown worlds astronomers had expected. Io's crust was painted in yellows, oranges, and reds, like a canvas splashed with sulfur. It didn't look like the battered, cratered moons people were used to. It looked fresh, as though it had been resurfaced recently. Scientists were puzzled, but the real shock came a little later, when navigational images showed something even stranger: plumes rising above the surface. A scientist named Linda Morabito noticed them while working with Voyager's navigation team. At first, the feature on the image looked like a smudge, or perhaps an error, but closer inspection revealed it was real: a massive eruption shooting material hundreds of kilometers into space. Io was erupting before the spacecraft's eyes. It was the first time active volcanoes had ever been seen beyond Earth. As Voyager sent back more images, the scale of Io's fury became undeniable. Giant calderas, lava flows stretching for miles, and fountains of molten rock were spread across the moon. Some plumes reached heights of nearly 200 miles, ejecting sulfur and other materials far above the surface, so high that they sometimes fell back down in arcs, visible to the spacecraft's cameras. Instead of being shaped by ancient impacts, Io was being constantly remade by its own internal fire. The discovery was not only surprising but deeply confusing. How could a small moon so far from the Sun have enough heat for such intense geological activity? Earth's volcanism was understood to come from radioactive decay deep within the planet and from the residual heat of its formation. But Io was smaller than Earth's moon. It should have cooled long ago. The answer came from its relationship with Jupiter. Io's orbit is locked in a gravitational tug-of-war. It is caught between Jupiter's immense pull and the gravitational influences of its neighboring moons, Europa and Ganymede. This three-body interaction forces Io's orbit to remain slightly elliptical rather than circular. Each time it swings closer to Jupiter, the planet's gravity stretches Io's interior, and when it swings away, the stress releases. The constant flexing of Io's insides creates enormous friction, generating heat on a scale so vast it melts the moon's interior rock. That heat escapes through volcanoes, endlessly reshaping the surface. Voyager's discovery of Io's volcanism revealed that energy in the solar system doesn't always come from sunlight. Tidal heating, this gravitational kneading of a world's interior, was a new and powerful mechanism that could fuel geologic activity even in the outer solar system. It meant moons could be warm and dynamic even when far from the sun's rays. If one small moon could be this active, what might others hide? Io's volcanoes didn't just rewrite the story of one moon, they expanded the possibilities for countless others across the solar system. The scale of the eruptions also had effects that reached beyond Io itself. Voyager's instruments detected material from Io's volcanoes escaping into space and forming a vast cloud of charged particles around Jupiter. This material helped to feed Jupiter's already immense magnetosphere, making the space environment around the planet even more hostile. In a sense, Io was not just shaping its own surface, but actively influencing the entire Jovian system. Visually, the discoveries were just as striking. The images of Io looked like no other place humanity had ever seen. Vast lakes of molten sulfur, mountains taller than Everest, and volcanic fountains made it a landscape of extremes. Where Earth's volcanoes are dramatic but limited, Io seemed to be covered in them, an entire world defined by eruptions. It was a planet-sized laboratory for geology, showing what happens when tidal heating reaches its peak. The notion of volcanoes blasting material into space on a distant moon was something out of science fiction, and yet Voyager had shown it was real. For scientists, it was both thrilling and humbling. Decades of assumptions about how worlds behaved had been overturned in a single flyby. Io's discovery also carried implications for the search for life. While its volcanic surface is likely too hostile for life as we know it, the mechanism behind its heat suggested that other moons, perhaps less extreme, could host warm environments. The idea that life might exist not because of sunlight but because of internal heat was a shift in thinking. Without Io, the path to considering places like Europa or Enceladus as potential habitats might have been far slower. The Voyager missions had set out to study planets, but with Io they revealed that moons could be just as dramatic, just as complex, and just as important. A world once thought to be a cold, dead rock was transformed into the most volcanically active body in the solar system. It was a reminder that exploration is not just about confirming what is expected, but about being ready to be astonished. Europa's hidden secret, the first clues of a subsurface ocean. When Voyager turned its cameras toward Europa, scientists saw a world covered in strange streaks, fractures, and chaotic patterns that looked as though someone had taken a sheet of ice and cracked it with their hands. The surface appeared smooth, almost too smooth, with very few signs of large impact scars. This was unusual. In the cold outer solar system, where geological activity was thought to be minimal, a world without heavy cratering meant something had reshaped its surface recently. For planetary scientists, the most striking aspect of Europa's surface was its resemblance to sea ice on Earth. The jagged ridges, the broken plates, and the darker material that seemed to ooze up through cracks all looked eerily familiar to researchers who studied ice sheets in Earth's polar regions. It suggested that Europa's outer layer was not solid rock, but rather water ice, and beneath that there might be something moving and shifting. If the crust was truly floating, like pack ice on an ocean, then Europa might not be a frozen dead world after all. It could be hiding a global sea beneath a shell of ice, a possibility that immediately captured both scientific curiosity and the imagination of anyone thinking about the search for life beyond Earth. Before Voyager, no one had seriously considered that Europa might harbor liquid water. The Moon orbits far from the Sun, too distant to receive enough heat for surface water to remain unfrozen. Temperatures on its icy exterior dropped to around negative 160 degrees Celsius, cold enough to freeze nearly everything solid. Yet the strange surface features implied something warmer and more dynamic below. The smoothness of Europa's surface, especially when compared to the battered, cratered surfaces of other Jovian moons, suggested it was geologically young. Instead of billions of years old, the visible surface of Europa might have been shaped only tens of millions of years ago, a blink of an eye in cosmic terms. Something was constantly resurfacing the Moon. Voyager's images allowed scientists to begin connecting the puzzle. Europa's closeness to Jupiter meant it was caught in a constant gravitational tug-of-war. Along with its sibling moons Io and Ganymede, Europa was locked into a resonance. The effect was tidal heating, the same process responsible for Io's furious volcanism, though on Europa it played out differently. Instead of turning the interior into a molten sea of magma, tidal forces could generate enough heat to keep a vast ocean of water beneath the crust from freezing solid. Voyager had uncovered the first sign of this possibility, a world of ice behaving more like a shell over something alive and moving. The cracks and streaks became the first evidence for scientists to imagine a hidden ocean world. Some ridges looked as though blocks of ice had broken apart, drifted and then frozen back together. almost exactly like icebergs on Earth's polar seas. Darker streaks cutting across the Moon might have been created when subsurface material seeped upward through the cracks, leaving stains on the icy surface. Though Voyager lacked the instruments to confirm what lay beneath, the images spoke louder than measurements could. They painted a picture of a moon that was not dead but restless, concealing a secret ocean in the darkness below its frozen shell. This was revolutionary. Until that moment, the search for life in the solar system had been mostly confined to places like Mars, where liquid water might have once existed on the surface. But if Europa had an ocean, then the rules changed completely. A world did not need to be warm and Earth-like to host liquid water. Heat from tidal flexing, rather than sunlight, could sustain an ocean beneath miles of ice. That single realization, sparked by Voyager's flyby, expanded the idea of habitable zones beyond the traditional Goldilocks zone around stars. Life might find a home in places long thought impossible. Scientists began re-examining Europa with fresh eyes. They asked how thick the icy crust might be, how deep the ocean could extend, and whether hydrothermal activity at the ocean floor might provide energy for life. If vents existed, like those on Earth's seafloor, they could create ecosystems independent of sunlight, feeding on chemical energy instead. The idea that a distant moon of Jupiter could host something similar to Earth's deep ocean life was a thrilling and unsettling thought. For the first time, researchers began to consider that we might not need to travel to other planets to find extraterrestrial life. It might be hidden within the frozen moons of our own solar system. Voyager did not solve these mysteries, but it gave us the first real glimpse. The cracked surface was a doorway into a new way of thinking about worlds beyond Earth. Later missions, such as Galileo in the 1990s, would provide stronger evidence by detecting signs of a conductive layer beneath the ice, consistent with a salty ocean. But it all began with those initial snapshots that Voyager sent back. The public was equally fascinated. The idea of an alien ocean hidden beneath an icy shell felt like the plot of a sci-fi novel. Yet here it was, supported by real evidence from Voyager's cameras. People imagined what creatures might swim in the darkness beneath Europa's ice. Artists drew scenes of explorers drilling through the crust to release geysers of water, while others speculated about entire ecosystems, evolving in a place that had never seen sunlight. Voyager's discovery had ignited not only scientific research, but also a surge of imagination that would shape how we think about the search for life in space. Even today, decades after Voyager's encounter, the cracked surface of Europa remains one of the most inspiring images in planetary science. The questions it raised still drive new missions, like the upcoming Europa Clipper, designed to investigate the thickness of the ice, the chemistry of the surface, and the possibility of water plumes erupting into space. Every modern step in exploring Europa can trace its origins back to that first moment when Voyager revealed a surface that looked broken but alive. The Ring Giant. How Voyager transformed our understanding of Saturn. For hundreds of years, Saturn had been a symbol of wonder in the night sky. Through telescopes, its great rings appeared as delicate, mysterious bands encircling the pale yellow planet. Galileo first saw them in 1610, though his crude telescope made them look more like strange ears sticking out from the planet's sides. Over the centuries, astronomers learned they were rings, and better instruments revealed them in sharper detail. Yet despite all the progress, Saturn still appeared smooth and almost unreal. Its rings seemed simple and serene, its planet calm and majestic. Voyager was about to change that picture forever. When Voyager approached Saturn in the early 1980s, for the first time, humanity could look closely at this giant world and its iconic rings. The rings were not just a few broad, simple bands. They were made up of countless thin structures, sharp divisions, and intricate waves. What had seemed smooth from Earth turned out to be a system of dizzying complexity. Instead of solid sheets, the rings were composed of billions of icy particles, ranging in size from grains of sand to house-sized boulders, each orbiting Saturn in delicate harmony. Voyager's images showed that the rings were divided into thousands of narrow strands, almost like the grooves on a vinyl record. Some of these strands twisted into braids, while others showed strange wave-like ripples running through them. The level of detail was breathtaking and completely unexpected. Many of these patterns were caused by Saturn's many moons, whose gravitational pull disturbed the particles, creating ripples and gaps. The most famous of these gaps, the Cassini division, turned out to be not empty at all, but filled with faint, delicate ringlets. Voyager revealed the rings to be a living, changing system, shaped constantly by the gravitational dance between Saturn and its satellites. Scientists soon realized that the rings were not just ornaments around Saturn, but a laboratory for studying how gravity works on cosmic scales. The shepherd moons, small satellites orbiting near or within the rings, acted like cosmic sculptors. Their pull kept ring edges sharp, carved out lanes of emptiness, and even maintained the twisted braids of certain bands. The physics behind these interactions mirrored the same forces that shape galaxies and planetary systems. By studying Saturn's rings through Voyager's lens, researchers could glimpse the processes that built solar systems billions of years ago. As Voyager drew closer, it also turned its instruments toward Saturn itself. What had seemed like a bland, featureless surface from Earth telescopes now came alive with detail. Saturn's atmosphere, dominated by hydrogen and helium, was revealed to be a restless world of storms, winds, and massive weather systems. Voyager discovered jet streams racing around the planet at hundreds of meters per second, far faster than anything seen on Earth. The smooth yellow face of Saturn was, in truth, a churning canvas of clouds and bands. One of the most striking discoveries was the presence of enormous storms, some stretching thousands of kilometers across. Voyager captured the drama of Saturn's turbulent weather, including storm systems that dwarfed our entire planet. These storms formed and dissipated with a rhythm scientists, driven by the planet's deep atmosphere and rapid rotation. Saturn was no longer just a graceful gas giant. It was a dynamic, unpredictable world with a climate system as complex as anything in the solar system. Voyager also taught us that Saturn's atmosphere was layered, with deeper clouds made of ammonia and water hiding beneath the upper haze. By studying the way light reflected off the planet, scientists could infer details about its chemistry and structure. They learned that Saturn was alive with movement from its core outward, with energy driving storms and shaping cloud bands. The moons of Saturn were another surprise that Voyager brought into sharp focus. Before the mission, many of these moons were little more than points of light, tiny dots barely resolved even by Earth's best telescopes. Voyager revealed them as diverse and fascinating worlds in their own right. Enceladus appeared as a bright, icy sphere, hinting at mysteries that would only later be fully appreciated. Mimas, with its massive crater Herschel, looked like a cosmic version of the Death Star. Triton, Saturn's largest moon, appeared wrapped in a thick orange haze that completely obscured its surface, a shroud that stirred curiosity about what lay beneath. Perhaps most unexpectedly, Voyager revealed just how much the moons interacted with the rings. Some moons created sharp boundaries by pulling material into or out of certain regions, while others generated spiral density waves, patterns that rippled outward through the ring particles. It was as though the entire system of Saturn, planet, rings and moons, was engaged in a constant dialogue, with each part influencing the others in ways both subtle and dramatic. The fine structure of the rings suggested they were not ancient relics from the birth of the solar system, as once thought, but perhaps much younger. Their sharpness and brightness hinted that they could be relatively fresh, possibly formed by the breakup of a moon or comet in the recent past. This raised new questions about how long rings could last, and whether Saturn's beauty might one day fade as the rings disperse. The planet's rings, seen up close for the first time, looked almost unreal in their precision and elegance. Photographs showing the planet with its rings casting shadows across its atmosphere became instant icons, reinforcing Saturn's reputation as the jewel of the solar system. What people didn't always realize was that behind the beauty lay a newfound complexity, a dynamic world with layers of mystery waiting to be explored. Voyager's encounter with Saturn revealed that gas giants were worlds with intricate weather systems, capable of producing some of the most extreme atmospheric conditions in the solar system. It showed that rings were not solid, featureless structures, but vibrant, shifting arenas where gravity shaped matter into breathtaking patterns. And it turned moons once thought unremarkable into destinations of their own, each one adding another piece to the puzzle of how Saturn's system works. The Cassini spacecraft, launched in the 1990s, built on Voyager's foundation, diving deeper into the mysteries of Saturn's rings, atmosphere, and moons. Cassini's mission would not have been possible without the trailblazing work of Voyager, which revealed just how rich and complex Saturn truly was. Every later discovery, from Titan's methane lakes to Enceladus's water plumes, traced its roots back to those first astonishing close-ups sent by Voyager decades earlier. Titan's mystery atmosphere, a hint of prebiotic chemistry. Titan, larger than Mercury and second only to Ganymede in size, was wrapped in a mystery that had fascinated astronomers for decades. Through Earth-based telescopes, Titan appeared as a faint, fuzzy orange ball, its surface completely hidden behind a thick haze. Many had speculated about what lay below, but no one truly knew. As Voyager flew past Saturn, it turned its attention to Titan. What it found wasn't a barren, airless rock like so many other moons. Instead, Titan possessed a thick, nitrogen-rich atmosphere denser than Earth's. That alone was astonishing. Of all the moons orbiting planets, only Titan held on to such a massive blanket of gas. But the surprises went deeper still. Voyager detected methane, ethane, and a wide variety of complex hydrocarbons in the air, molecules made of carbon and hydrogen, the building blocks of life's chemistry. The haze that gave Titan its orange glow was created by these very compounds. Ultraviolet light from the sun, though weak at Saturn's distance, was enough to break apart methane in the upper atmosphere. Those fragments recombined into heavier organic molecules, which clumped together into tiny particles. Over time, these particles drifted downward, thickening into layers of smog that wrapped Titan in an impenetrable veil. This was no ordinary atmosphere. It was a chemistry lab frozen in time, where simple molecules were constantly being transformed into more complex ones. On early Earth, before life began, the atmosphere may have been rich in similar compounds. Lightning, ultraviolet light, and other energy sources could have driven reactions that built more and more complex molecules, eventually leading to the chemistry of life itself. On Titan, Voyager seemed to be witnessing a version of that same process still playing out, billions of years later. In a way, Titan offered a window into Earth's distant past. Yet, for all its revelations, Voyager also highlighted the limits of its own tools. Its cameras could not see through Titan's haze, leaving the surface hidden in mystery. Was there liquid methane pooling in lakes or seas? Were there oceans of water buried beneath the crust? Or was Titan simply a frozen wasteland, smothered under its smoggy skies? Voyager could not provide those answers, but by raising the questions, it transformed Titan into one of the most compelling worlds in the solar system. No other moon had an atmosphere anything like it. While other moons of Saturn, like Enceladus or Mimas, showed striking geology or intriguing surfaces, Titan stood apart as a world that felt almost planetary in scale and complexity. With its dense air, organic chemistry, and sheer size, Titan was not just another satellite. It was a world with its own story. The discovery of so many organic compounds immediately sparked excitement in the scientific community. Organic chemistry is the foundation of life, but it is not exclusive to living systems. Voyager had shown that such molecules could form naturally under the right conditions, without any biology at all. That realization pushed scientists to think more broadly about where life might emerge in the cosmos. If Titan could generate these compounds on its own, perhaps similar chemistry was happening on other planets, moons, or even interstellar clouds. The universe, it seemed, might be full of the raw ingredients for life. At the same time, Titan challenged assumptions about where habitability might be found. Traditionally, astronomers looked for planets in the habitable zone around stars. Titan was far outside that zone, in a region of deep cold where water was frozen harder than rock. Yet here was a moon with a thick atmosphere and remarkable chemistry. It was alien, but it was familiar in ways that made it irresistible to study. Winds blew through its upper layers, redistributing haze and shaping cloud patterns. Temperatures dropped dramatically as altitude increased, creating layers of different densities and compositions. The moon even had a greenhouse effect, though far weaker than Earth's, which helped trap heat and shape the balance of its climate. These details painted a picture of a world far more complex than anyone had imagined. Because Voyager could not penetrate the haze, Titan remained an enigma, a world of tantalizing hints, but no clear answers. Scientists knew it demanded a return. That return came in the form of the Cassini-Huygens mission, launched in 1997, which spent more than a decade orbiting Saturn. Cassini carried the European-built Huygens probe, which parachuted through Titan's atmosphere in 2005, revealing lakes of liquid methane, river channels, and a surface shaped by rain and erosion. What Voyager had suggested, Cassini confirmed in stunning detail. Even today, Titan remains a place of extraordinary importance in planetary science. The compounds Voyager detected are still being studied, their chemistry simulated in laboratories to understand how life's building blocks might arise naturally. Titan continues to serve as a model for how complex chemistry unfolds in cold, alien environments. And as missions are planned for the future, like NASA's Dragonfly rotorcraft, set to explore Titan's surface in the coming decades, they carry forward the legacy that began with Voyager's flyby. Uranus tilted sideways, a planet that defied every expectation. Voyager 1 and Voyager 2's trajectories diverged after the Saturn encounter. Voyager 1 was given a close pass by Titan, as it was too compelling a target to skip. The only way to learn more about it was to swing Voyager 1 close enough to collect data. That choice, however, meant Voyager 1's path bent sharply upward, sending it out of the plane of the solar system. The detour effectively ended its chances of reaching Uranus or Neptune. Voyager 1 became the pioneer of deep space, destined to leave the planetary tour behind after Saturn. Voyager 2, on the other hand, had a more open path. Because it did not make such a drastic course adjustment for Titan, it remained on a trajectory that could carry it onward to Uranus and Neptune. It was never guaranteed at launch that it would actually make the trip. Each extension of Voyager 2's mission required justification. Why continue to operate an aging spacecraft millions of kilometers from home? The answer again and again was that no other opportunity like this would ever present itself in human lifetimes. So Voyager 2 pressed on. After Saturn, it became the only emissary to head toward the strange and distant world of Uranus. When Voyager 2 arrived at the planet in January 1986, it was entering uncharted territory. Everything scientists knew about the planet could be condensed into a handful of blurry telescope images and basic orbital data. It was the forgotten giant of the solar system, faint and far away, often overshadowed by its more dramatic neighbors like Jupiter and Saturn. Yet as the spacecraft closed in, one of Uranus's most bizarre features came into sharp focus: its tilt. Unlike every other planet, Uranus was tipped so far over that it essentially rolled around the Sun on its side. Uranus's axis is tilted about 98 degrees relative to its orbit. If Earth's tilt is responsible for the familiar march of seasons, then Uranus's tilt produces something utterly alien. For long stretches of its 84-year orbit, one pole points almost directly at the Sun, while the other sinks into prolonged darkness. Each pole spends about 42 years basking in constant daylight, or locked in unbroken night, before the cycle reverses. Voyager 2's encounter came when the southern hemisphere was in full sunlight, its poles staring straight at the Sun, as if challenging every assumption scientists had about how planets should behave. The consequences of such an orientation are dramatic. On Earth, the sun rises and sets every day, varying slightly with the seasons. On Uranus, however, the concept of day and night stretches into extremes. Near the poles, there are decades-long stretches where the sun never leaves the sky or never rises at all. Even in the middle latitudes, the path of the sun across the sky takes on bizarre arcs, nothing like the predictable patterns we know. Seasons on Uranus are therefore unlike those on any other planet. Instead of gradual shifts of climate and sunlight, Uranus experiences long, strange epochs of light and dark, with abrupt transitions as the planet continues its sideways march around the Sun. When Voyager 2 began sending back images, scientists were eager to see what this strange tilt had done to Uranus's atmosphere. Many expected to find violent storms and dramatic cloud patterns, stirred up by the wild extremes of solar heating. After all, Saturn's bands and Jupiter's swirling storms showed what gas giants could do with much less provocation. But Uranus surprised everyone. The planet's face was eerily featureless, a pale bluish-green ball with almost no obvious structure. To the untrained eye, it looked more like a painted marble than a living world. The lack of atmospheric detail puzzled scientists. How could a planet with such extreme seasons appear so calm, so uniform, almost lifeless? Part of the answer lay in Uranus's distance from the Sun. At nearly 3 billion kilometers away, it receives very little sunlight compared to the inner planets. The energy available to drive storms and atmospheric patterns is minimal. Moreover, Uranus emits very little internal heat. Jupiter, Saturn and Neptune all radiate more energy than they receive from the Sun, powered by heat leaking from their interiors. This extra energy stirs their atmospheres, creating the banded structures and storms that make them so dynamic. Uranus, however, gives off almost no excess heat. Its internal furnace is either weak or long since cooled. Without that extra push, its atmosphere remains muted, its weather subdued to a degree unseen on other giants. Careful analysis of Voyager 2's images revealed subtle cloud features and wind patterns that hinted at activity below the bland exterior. High-altitude hazes stretched across the atmosphere masked deep emotions. Later telescopes, using infrared and other wavelengths, would uncover evidence that Uranus's atmosphere was far more active than Voyager's visible light cameras suggested. Voyager 2's flyby, however, gave the first tantalizing glimpse of this mystery, a world that appeared deceptively calm while hiding unseen dynamics. The tilt of Uranus raised even deeper questions about its origin. How does a planet end up rolling on its side? The leading theory is that in the early days of the solar system, Uranus suffered a catastrophic collision. Perhaps a protoplanet the size of Earth slammed into it, knocking it askew. Such a colossal impact could explain the extreme tilt and perhaps even the lack of internal heat if much of the planet's energy escaped in the aftermath. Other theories suggest multiple smaller impacts gradually tipped Uranus over, or that gravitational interactions with giant neighbors destabilized its axis. Whatever the cause, the result was a planet that broke every rule about planetary orientation. The tilt also influenced Uranus's magnetic field. Unlike Earth, where the magnetic field is roughly aligned with the planet's spin axis, Uranus's field was tilted by nearly 60 degrees, an offset from the planet's center. It did not behave like the neat, symmetrical dipoles scientists were familiar with. Instead, it was lopsided and irregular, wobbling in strange patterns as Uranus rotated. Combined with the planet's sideways spin, this created a magnetic environment that was in constant flux. The moons of Uranus also bore the imprint of this tilted world. Voyager 2 discovered that the planet's satellites orbited in a plane aligned with its equator, meaning they too were tilted sideways relative to the Sun. Their orbits were locked into Uranus's strange geometry, circling a planet that itself rolled around its path. For billions of years, these moons had lived under the bizarre seasons of their parent world, experiencing cycles of light and darkness that no other moons in the solar system endured. The patchwork landscapes of Miranda and the dark surfaces of other moons may have been shaped, at least in part, by the odd tilt of Uranus. The effect on the rings was equally fascinating. Unlike Saturn's grand rings, Uranus's were thin, dark and narrow, but they shared the planet's tilted orientation. Voyager 2's cameras revealed them edge-on, faint stripes across the void. Their existence in such a tilted system posed questions about their stability and origins. How could such delicate structures survive billions of years of gravitational disruption? The answer was still uncertain, but Voyager's observations proved they were real, intricate, and bound up in Uranus's sideways nature. For centuries, humans had assumed planets would all more or less follow the same patterns: spinning upright, showing familiar kinds of weather, orbiting in predictable harmony. Uranus shattered those assumptions. It was a reminder that the solar system is not a place of uniformity, but of wild variety. The tilted world left scientists with more questions than answers. What exactly caused its sideways orientation? How does such an axial tilt affect the long-term evolution of a planet's atmosphere and interior? What secrets are still hidden beneath the bland haze of its skies? Decades later, astronomers still puzzle over these questions, using data from Voyager 2 combined with modern telescopes to piece together the mysteries. Yet even now, much of Uranus remains a blank spot in our knowledge, a giant that defies easy classification. The forgotten treasure: how Voyager showed Neptune was more than a blue speck. When Voyager 2 left Uranus behind, its mission had already exceeded the original expectations. It had shown us a sideways planet, a set of rings and satellites that nobody had ever really seen before. But one more destination lay ahead. Neptune, the eighth planet from the Sun. For centuries it had been nothing more than a faint blue dot in telescopes, an object so distant that even its basic details were hard to pin down. As the spacecraft drew closer in the summer of 1989, scientists prepared for a world they assumed would be quiet. After Uranus's bland, featureless atmosphere, expectations were modest. Neptune was even farther from the Sun, receiving less than half the sunlight Uranus did. It seemed logical that its atmosphere would be subdued, its features faint, its surface calm and uneventful. Yet as Voyager 2 began sending back its first images, the planet defied all assumptions. Neptune was alive with weather, winds and storms of staggering scale. The most dramatic discovery was a dark oval spot near Neptune's equator, later called the Great Dark Spot. It was the first major storm system ever seen on the planet, and it immediately invited comparison with Jupiter's Great Red Spot. Like its Jovian cousin, Neptune's storm was huge, large enough to swallow Earth, and it spun with fierce energy in the upper atmosphere. But unlike Jupiter's centuries-old storm, the Great Dark Spot appeared transient. Voyager's brief encounter captured it in full force, but later observations from the Hubble Space Telescope showed it had disappeared within just a few years. Neptune's weather, it seemed, was more volatile than people had imagined. The winds that drove these storms shocked scientists even more. Voyager's instruments measured speeds of up to 2,100 kilometers per hour, the fastest atmospheric winds recorded on any planet. For comparison, Earth's strongest hurricanes reach wind speeds of around 250 kilometers per hour. Neptune's gales were nearly 10 times faster, despite the planet being so far from the Sun that little solar energy was available to stir its atmosphere. The source of this energy remained a mystery. Perhaps Neptune, like Jupiter and Saturn, radiated more internal heat than it received, fueling storms deep inside its clouds. Whatever the cause, it was clear that distance from the Sun did not mean stillness. Neptune was a dynamic world, and Voyager had revealed its restless nature. Voyager also showed that Neptune's blue color, long noted from telescopes, was not just a vague tint, but a vivid feature of its atmosphere. The planet's hue came from methane gas high in the atmosphere, which absorbed red light and reflected blue. But the color was not uniform. Voyager's cameras picked out subtle bands, wisps of clouds and smaller storm systems scattered across the surface. One particularly bright feature, dubbed the Scooter, raced around the planet faster than the Great Dark Spot itself. The Scooter was a cloud system of unknown origin, a bright beacon cutting across Neptune's deeper blue backdrop. In a matter of weeks, the planet went from a mysterious speck to a place with its own character, its own storms, and its own distinct personality. The rings of Neptune, once only suspected, were confirmed by Voyager's passage. Telescopic hints of faint arcs around the planet had puzzled astronomers for years, but Voyager provided the first clear evidence. Unlike Saturn's majestic rings, Neptune's were faint, narrow, and clumpy, consisting of dark material that reflected little light. Some appeared incomplete, forming arcs instead of full circles. The explanation, as Voyager revealed, lay in the presence of small shepherd moons whose gravity corralled the particles into confined regions. The rings were fragile, tenuous structures, unlike anything seen before. They showed that rings were not just a feature of Saturn, but a more widespread phenomenon among the giant planets. Perhaps the most surprising revelation came not from Neptune itself, but from one of its moons. Triton, the largest of Neptune's satellites, was unlike any other body Voyager had encountered. It orbited the planet in a retrograde direction, opposite to Neptune's rotation, suggesting it was a captured object rather than one that formed in place. Voyager's close-up images showed an icy world with a pinkish hue, streaked with dark markings and dotted with strange, smooth plains. The flyby itself was a feat of precision. Neptune lay nearly 4.5 billion kilometers from Earth, so far that radio signals from Voyager took over 4 hours to reach home. Yet the spacecraft threaded its way through the planet's system with accuracy measured in tens of kilometers. The trajectory carried it close to Neptune's cloud tops, before swinging past Triton, capturing as much data as possible before heading off toward interstellar space. The encounter was brief, lasting only days, but the images and measurements it returned would fuel decades of research. For the public, Neptune had been a vague and distant presence, the last of the classical planets and the hardest to study from Earth. Suddenly, the farthest known planet in the solar system had come alive in human imagination. In some ways, the encounter with Neptune felt like the closing of a chapter. Voyager 2 had completed the grand tour, visiting all 4 of the outer giants, something no spacecraft had done before or has done since. The images of Neptune and Triton became a final treasure, the last great planetary encounter of the 20th century. What had once been just a blur at the edge of visibility was now a world with storms, winds, rings and moons, its own system of mysteries waiting for future explorers. Triton's alien landscape, cryovolcanoes in the deep cold. Triton's surface looked alien in a way that went beyond the already strange variety of moons encountered earlier in the journey. Unlike the crater-covered faces of most small bodies, Triton displayed vast, relatively smooth plains, broken by fissures, ridges, and strange polygonal patterns. There were regions that seemed to have been resurfaced, erasing old scars, as though the moon had renewed itself. This suggested a form of geological activity, something that no one had expected to find so far from the Sun. The surprise deepened when Voyager detected geysers erupting from Triton's surface, jets of nitrogen gas and icy dust blasting upward and drifting for kilometers in the thin atmosphere. In an instant, the concept of a frozen dead world collapsed, replaced by the idea of an active moon sculpted by forces utterly different from Earth's, or even those of the giant planets. These geysers were unlike the volcanic eruptions seen on Io near Jupiter. Instead of molten rock, Triton's cryovolcanoes released cold material, driven not by heat from a molten core, but by more subtle energy sources. One possible mechanism involved sunlight, weak though it was at Neptune's distance, penetrating a thin surface layer of frozen nitrogen. Trapped heat could build up beneath the ice until it caused pressure to rise, releasing a geyser into the sky. Another explanation pointed to tidal forces, as Triton's unusual orbit around Neptune could generate internal friction and heat. Either way, the phenomenon introduced the concept of cryovolcanism to planetary science, volcanic activity driven by ice rather than fire. This broadened the definition of what it meant for a world to be active. In the outer reaches of the solar system, ice itself could behave like rock, cracking, flowing and erupting in slow but dramatic ways. Voyager's images of Triton revealed towering cliffs, some rising several kilometers high, cutting across its landscape. There were terrains marked by cantaloupe terrain, a nickname scientists gave to the strange, dimpled texture found on parts of its surface. These regions had no close analogue elsewhere, making them one of the most puzzling geological features ever seen. It looked as though the Moon's crust had been pushed and pulled in ways that defied easy categorization. Patterns suggested processes still ongoing, perhaps even recent on a geological timescale. Unlike the heavily cratered surfaces of ancient bodies, Triton's young-looking face indicated that it had been resurfaced multiple times. In effect, the Moon was rewriting its own history, erasing old marks and replacing them with new ones. If such a distant and cold moon could sustain geological processes, then perhaps many other icy worlds could as well. This opened the door to speculation about the outer solar system as a whole. Moons orbiting Saturn, Uranus, or even smaller bodies in the Kuiper Belt might also host hidden activity beneath their icy shells. Triton became a prototype for a new class of worlds, icy yet alive, frozen yet dynamic. It changed how scientists thought about energy in the cosmos. Heat did not have to come only from a nearby star. It could be generated internally, sustained by orbital mechanics or by hidden chemical reactions. Another astonishing aspect of Triton was its retrograde orbit. Unlike most large moons, which circle their planets in the same direction the planet rotates, Triton moved in the opposite direction around Neptune. This meant it had not formed alongside Neptune, but had likely been captured from elsewhere. Many scientists believe Triton was once a Kuiper Belt object, a distant icy body similar to Pluto that wandered too close to Neptune and was ensnared by its gravity. Over time, this capture altered both Triton's path and its internal dynamics, perhaps fueling the geological activity Voyager observed. This origin story gave Triton a dual identity, part of Neptune's system, yet also a relic of the solar system's outermost frontier. Voyager's flyby was a first glimpse into the realm of bodies that lay beyond Neptune, a preview of the Kuiper Belt before it had even been discovered. Triton's thin atmosphere was another revelation. Voyager measured it and found it composed primarily of nitrogen, with traces of methane. While the atmosphere was tenuous compared to Earth's, it was thick enough to sustain winds and to play a role in shaping the surface. Plumes from the geysers were seen drifting sideways, carried by these winds, leaving dark streaks across the icy plains. Even in the deep freeze of Neptune's orbit, there was movement in the air, cycles of condensation and sublimation, and a dynamic interplay between surface and atmosphere. Triton was proving itself to be a complete world, with systems as complex and surprising as any found closer to the Sun. The cliffs and fault lines on Triton hinted at massive upheavals in its past. Entire portions of the crust seemed to have broken and shifted, evidence of stresses that had built up and released. Some scientists proposed that Triton once had a liquid ocean beneath its icy shell, one that might still exist in some form today. If true, this would place Triton among the growing list of worlds with potential subsurface oceans, environments that could, at least in theory, harbor the chemistry of life. The idea that such possibilities existed so far from the Sun was staggering. The encounter with Triton was brief, as all of Voyager's flybys were, but its impact was profound. Scientists were left with far more questions than answers. Why was Triton still active? How much of its surface was being reshaped today? Could a hidden ocean lie beneath its crust? And perhaps most intriguingly, what did its existence say about the countless other icy bodies scattered beyond Neptune, waiting to be explored? The end of the tour, how Voyager said goodbye to planetary science. For over a decade, the two Voyagers had been ambassadors to the unknown, moving from one world to the next, each flyby a carefully choreographed encounter that delivered shocks, wonders, and mysteries. After Neptune, however, there were no more major worlds waiting. Pluto, still officially considered the ninth planet at the time, was far off to the side, unreachable with the spacecraft's trajectory. With that final close look at Triton and Neptune, the planetary exploration chapter of Voyager's mission drew to a close. For those who had dedicated years of their lives to planning encounters, there was a bittersweet quality to this moment. Planetary science had been the heart of Voyager, its purpose and its triumph. The images of Jupiter's great red spot, Saturn's rings, Uranus's tilted axis, and Neptune's roaring winds had not only advanced science, but also captured the imagination of millions. The fact that it was over, that there would be no more flybys, no new planetary landscapes revealed by Voyager's cameras, felt almost like a farewell tour. And yet, as engineers and scientists gathered in control rooms to monitor the spacecraft, it became clear that the mission was not ending. It was simply changing. The spacecraft still worked, still sent back signals across billions of kilometers, and still had instruments capable of probing the cosmos. NASA's planners understood this moment as a turning point. The Grand Tour had reached its natural end, but Voyager had become something more than a planetary probe. With the last major encounter behind it, the spacecraft could now focus on an even larger frontier, the edge of the Sun's domain itself. This was not a part of the original plan in 1977, when both Voyagers were launched. The primary mission had been planetary exploration, but the fact that the spacecraft had survived and was still functioning after so many years opened a door to a new kind of exploration. Instead of photographing alien worlds, Voyager would now measure the invisible boundaries of the solar system, boundaries that no spacecraft had ever crossed before. The solar system, after all, is not simply a collection of planets orbiting the Sun. Beyond Neptune lies a vast region filled with charged particles streaming outward from the Sun, known as the Heliosphere. This bubble of solar influence extends far past the last planets, creating a frontier between our Sun and the interstellar medium, the space between stars. No one knew how large the Heliosphere was, where it ended, or what conditions would be like at its edges. Voyager, equipped with instruments designed to measure magnetic fields, plasma waves, and cosmic rays, was perfectly suited to become humanity's first explorer of this realm. The planetary age of Voyager had ended, but the interstellar age had begun. During the planetary encounters, the excitement had centered on images, dramatic photos of moons and planets that dominated front pages and television screens. But once the cameras were powered down to conserve energy, Voyager's work became quieter, more abstract, yet no less profound. Instead of images, it returned streams of data, patterns of numbers that spoke of particle counts, radiation levels, and magnetic fields. These were harder for the public to visualize, but for scientists, they were just as thrilling. Voyager was no longer showing us new surfaces, but it was opening a path into the deep unknown. Built in the early 1970s, the Voyagers carried tape recorders, gold-plated copper record discs, and computers with memory measured in mere kilobytes. Yet they endured. Their RTGs, powered by the slow decay of plutonium, continued to provide electricity, though in decreasing amounts with each passing year. The fact that the spacecraft was still working at all, long past their expected lifespans, became part of the legend. Engineers had to carefully ration power, shutting down non-essential systems, squeezing every bit of performance from machines designed for a far shorter life. Each year was a gift. Each signal received across the void a reminder that humanity's reach extended farther than ever before. In a sense, this phase of the mission was even more daring than the planetary tour. The planets had been mapped from afar, their existence long known, their orbits predictable. But the edge of the Sun's influence was uncharted territory. It was a mystery how far the solar wind would stretch before giving way to the interstellar medium. Theorists had drawn models, some suggesting the boundary might lie just past Neptune, others placing it far beyond Pluto. Voyager was now on a voyage without a clear map, probing for a frontier no one could locate with certainty. Each measurement brought clues, shifts in particle density, changes in magnetic field orientation, signs that the spacecraft was approaching the limits of the Sun's protective bubble. Progress was measured, not in dramatic snapshots, but in subtle shifts across years. Voyager was moving into a place where no human-made object had ever gone, pushing the boundary of human presence further from home than anyone had imagined possible in the 1970s. For millennia, humanity had gazed at the visible planets with the naked eye, incorporating them into mythology, navigation, and science. The Grand Tour had extended that legacy, showing them up close, giving names and faces to worlds that had been little more than dots of light. Now, however, Voyager was moving into a region no human eye had ever seen, not even through the most powerful telescope. It was stepping beyond the solar system in a way that had no parallel in human history. Even as Voyager entered this new role, the world below continued to change. The Cold War, which had been raging when the spacecraft launched, was winding down. Technology on Earth was advancing at an astonishing pace, with personal computers, satellites, and the beginnings of the Internet reshaping daily life. Against this backdrop, the Voyagers were reminders of continuity. Launched in an earlier era, they remained steady voices from the edge of the solar system, their faint signals traveling across the decades and the distance, carrying the message that exploration never truly ends. The Final Push, a mission recast to explore the edge of the Sun's influence. The heliosphere is not like the surface of a planet or the orbit of a moon. It does not have sharp edges that can be seen from afar. It is a shifting frontier where the charged particles streaming outward from the Sun slowly lose their strength and meet the thin, scattered matter that fills the galaxy. No telescope could ever pinpoint its boundaries. Only a probe venturing into the deep could feel the changes in radiation, the shifting patterns of magnetic fields, and the slowing of the solar wind. The heliosphere had been modeled in countless ways, but no one agreed on its true size or structure. Its outer boundary, the heliopause, was thought of as a shield, protecting the solar system from much of the cosmic radiation that floods the galaxy. To cross it would be to step, however faintly, into interstellar space itself. That possibility gave Voyager's new mission an almost mythic quality. A spacecraft that had carried a golden record with greetings from Earth was now poised to cross the border between star and star. Particle detectors showed how cosmic rays grew stronger as the spacecraft moved farther from the Sun. Instruments designed to sense the faint oscillations of plasma picked up shifts in frequency, signs that the surrounding medium was changing. The magnetic field instruments recorded subtle alterations in direction, like a compass needle turning as it crossed into a new territory. Each of these changes was incremental, spread over years, but together they told a story of movement toward a great boundary. Systems that were once routine were now luxuries. The cameras, beloved by the public, had to be switched off. Instruments had to be carefully chosen to stay online, with others shut down forever. Heaters that had kept parts of the spacecraft warm were turned off, leaving instruments to endure temperatures far below freezing. The fact that so many continued to function despite these conditions was almost miraculous. As the spacecraft pushed farther outward, it revealed that the heliosphere was not smooth or simple. It was a dynamic place, with turbulence, waves, and complex interactions between solar wind and interstellar matter. The edge of the Sun's influence was not a clean line, but a frontier zone, like the surf of an ocean meeting a shore. Voyager was sailing into those waters, slowly, steadily, without a map. Every reading that made its way back to Earth across billions of kilometers expanded the human sense of where we lived and what surrounded us. When the instruments detected the solar wind slowing down, it suggested that Voyager was nearing the heliopause. When cosmic rays began to surge, scientists debated whether the spacecraft had crossed the boundary or was still within the Sun's protective bubble. There were false alarms and long waits, moments when it seemed the transition had come and then retreated. But with each new bit of evidence, Voyager was rewriting our understanding of the Sun's outermost frontier. Cosmic borderlands entering the Heliosheath. Beyond the planets and far past Pluto's orbit lay the Heliosheath, the outermost layer of the Sun's domain. This was a chaotic borderland where the solar wind, once a steady stream of charged particles racing outward at supersonic speeds, slowed down, grew turbulent, and began to mix with the thin gas and dust of the galaxy. It was here that the influence of our star began to falter. Astronomers and physicists believed that the solar wind, after rushing out for billions of kilometers, would eventually encounter the pressure of interstellar space and lose momentum. At that point, it would form a kind of shock wave, slowing abruptly and heating up. Beyond that, the wind would churn and twist in unpredictable ways, its once uniform flow broken into eddies and currents. For decades, this had been only a model, a set of equations suggesting that such a zone must exist. When Voyager reached this region, it confirmed what had long been guessed. The solar system had a border, and that border was alive with change. The transition was gradual, marked by signs that accumulated over time. The solar wind, once rushing past at hundreds of kilometers per second, slowed and thickened. Instruments designed to count particles showed sudden spikes and dips, evidence that the spacecraft was entering a more crowded and turbulent environment. Galactic cosmic rays began to leak in, no longer shielded as effectively by the sun's magnetic bubble. Each of these changes told scientists they were moving into new territory. Instead of the steady flow of solar particles, the spacecraft was buffeted by gusts and shocks. Magnetic field readings showed sudden swings, like a compass needle struggling to find true north. At times, the instruments detected bursts of plasma waves, as if the spacecraft were moving through invisible surf. Scientists had expected turbulence, but the sheer complexity of the Heliosheath surprised them. It was a vast, dynamic region, stretching billions of kilometers across, shaped by both the sun's outflow and the galactic environment pressing in from beyond. The Heliosheath was not just a scientific curiosity. It was the first line of defense against cosmic radiation, the shield that made the inner solar system more hospitable for life. By measuring how this shield behaved, Voyager helped scientists understand how stars carve out protective bubbles in the galaxy and how those bubbles interact with one another. In a way, the Heliosheath was as important a discovery as Io's volcanoes or Europa's ice. It revealed that the Sun, far from being a lone star, was an active participant in the cosmic environment, constantly negotiating with the galaxy around it. The journey through the Heliosheath was not quick. It stretched across years, even decades. For mission controllers, this was both a gift and a challenge. Each year that the spacecraft continued to function meant more data, more insight into this strange borderland. But it also meant more work to keep the aging machines alive. Engineers on Earth had to carefully manage power supplies. Commands sent from Earth took more than 12 hours to reach the spacecraft, and the signals returning were faint whispers, weaker than the light of a firefly seen from thousands of kilometers away. Yet those whispers carried knowledge no other instrument could provide. In some places, Voyager measured strong shocks, as if waves of solar wind had piled up against the galactic medium. At other times, it found regions of relative calm, where the solar wind seemed to flow smoothly again. Scientists began to speak of the Heliosheath as a kind of weather system with storms, lulls, and shifting currents. Each change offered new clues to the structure of the solar system's boundary. Voyager's passage through the Heliosheath also raised questions about what lay beyond. If this region was so turbulent, what would the final crossing into interstellar space look like? Would there be a clear sign, a sudden shift in particle counts, a dramatic change in magnetic fields? Or would the boundary prove as gradual as the entry into the Heliosheath itself? No one knew for sure. The spacecraft's data became the only guide, a slow accumulation of signals that hinted at answers but never revealed them all at once. Models of the solar system's outer edge had been drawn up for decades, but Voyager revealed features that no one had predicted. The sheer size of the Heliosheath, the unexpected strength of some shocks, the way cosmic rays seeped in more quickly than expected. All of these findings forced revisions to long-held ideas. Voyager was teaching researchers that the Sun's influence was both more complex and more fragile than they had thought. Our Sun is not a ruler of space. Its winds push outward, but eventually they yield. Its magnetic field shields us, but only to a point. Beyond that point lies the galaxy itself, vast, ancient, and full of incredible forces. The solar wind runs out, what Voyager taught us about the interstellar breeze. For as long as humans have studied the heavens, the sun has seemed eternal in its power, a source of endless light and energy. But Voyager revealed that even the sun's reach has its limits. For billions of miles, the solar wind streams outward, pushing against the galaxy, carving out a protective bubble around our solar system. Yet this flow cannot last forever. Voyager's passage into the deep frontier showed exactly where the sun's breath dies away and where another presence begins to dominate: the interstellar breeze. The solar wind had been detected much earlier, first inferred from the way comets' tails always pointed away from the sun, then later measured by spacecraft closer to Earth. It was known to be fast, supersonic, and relentless, but no one had ever followed it to its end. Voyager became the first messenger to report back on that distant frontier. As its plasma detectors and magnetometers listened to the signals of charged particles streaming around them, they captured the moment when the solar wind slowed, weakened, and finally surrendered to the galaxy beyond. The interstellar breeze wasn't a gale sweeping through space, but a thin stream of particles drifting between the stars. These atoms and ions, remnants of long-dead stars and interstellar clouds, had been wandering the galaxy for millions of years before crossing paths with Voyager. Detecting them was like catching the scent of another ocean while still standing on shore, a reminder that the world outside was vast and connected. For the first time, humanity was directly sampling the true environment of the galaxy, no longer filtered or shielded by the solar wind. The contrast between the solar and interstellar winds was dramatic. Within the heliosphere, the solar wind had been the dominant force, filling space with charged particles racing at hundreds of kilometers per second. Outside, however, Voyager found a different pressure pushing back. The interstellar medium was far thinner than even the best vacuum created in laboratories on Earth, but in the emptiness of space, its influence was profound. Voyager's data showed that this galactic wind was not only present, but dynamic, shifting and carrying with it the fingerprints of the broader galaxy, magnetic fields, cosmic rays and particles that had originated far beyond our star. For centuries, humans had imagined space beyond the solar system as empty, a cold vacuum stretching forever. The reality turned out to be far richer. Space between the stars was not nothing. It was alive with subtle currents and forces. Voyager's instruments revealed that the interstellar medium carried whispers of ancient stellar explosions. The remains of supernovae spread thin across the galaxy. The particles it detected were fragments of cosmic history, pieces of matter forged in furnaces light years away. The solar wind was a local force, carving out a bubble but ultimately confined by the broader ocean of the galaxy. The sun was revealed to be just one star among billions, its influence limited and shaped by pressures far greater than itself. The transition also brought mysteries. Scientists expected a smooth handoff between the solar wind and the interstellar medium, but Voyager's readings were anything but smooth. The instruments recorded strange spikes in plasma density, sudden fluctuations in magnetic field strength, and puzzling boundaries that seemed to ripple and shift. It was as if the edge of the solar system was a series of overlapping curtains, each one reacting differently to the push and pull of forces beyond. Voyager's passage revealed that the edge of the solar wind was not a static line, but a constantly moving frontier, shaped by both the sun's cycles and the conditions of interstellar space. One particularly striking feature was the way cosmic rays behaved at the boundary. Inside the heliosphere, the solar wind kept many of these high-energy particles at bay, deflecting or slowing them down. But beyond the point where the solar wind lost its strength, Voyager detected a sharp rise in cosmic ray intensity. It was as though a floodgate had opened, letting in the raw radiation of the galaxy. These measurements gave scientists new insights into how cosmic rays move through space, knowledge that was vital not only for astronomy, but for any future human journeys beyond the safety of Earth. The interstellar breeze wasn't coming directly toward us from the direction the solar system was traveling. Instead, Voyager found that the galactic particles approached at an angle, shaped by magnetic fields and flows on a scale larger than the solar system itself. This tilt hinted at vast structures in the interstellar medium, invisible threads of magnetism and pressure that guided particles across light years. In a sense, Voyager wasn't just detecting the galaxy's wind, it was glimpsing the unseen architecture of the Milky Way. For planetary scientists and astrophysicists alike, these discoveries transformed Voyager from a planetary mission into a galactic one. The spacecraft had bridged the gap between the local and the cosmic, and in doing so it opened up an entirely new field, interstellar science. No longer limited to speculation, this discipline now had direct evidence, carried back across billions of miles by the faint transmissions of a lone spacecraft. The measurements continued long after that first crossing, with Voyager sending back data that refined our understanding of the interstellar breeze. Each new transmission added another brushstroke to the picture of what lay beyond. The interstellar medium, once thought of as empty, was revealed to be alive with motion and history, and humanity, once confined to the imagination of maps and models, was now a participant in the exploration of the galaxy. Magnetic Whispers: How Voyager Mapped Invisible Forces of the Galaxy. Magnetism is one of those invisible forces that quietly governs the universe. On Earth, we experience it through compasses that point north, guiding explorers across seas and landscapes. In space, however, magnetism takes on a far larger role. It bends the paths of charged particles, shapes the movement of plasma, and even protects entire planets from the fury of solar winds. Voyager, carrying its slender magnetometer booms, became one of humanity's first explorers of this hidden architecture on a galactic scale. The magnetometer on Voyager worked in silence, measuring the faint tug and twist of magnetic fields as the spacecraft journeyed outwards. Inside the heliosphere, the Sun's magnetic field dominates. Carried outward by the solar wind, it spirals into space in what is called the Parker spiral, a vast corkscrew of magnetism that rotates with the turning Sun. Voyager's instruments felt this field grow weaker as it traveled further out, tracing its decline with precision. It confirmed that the heliosphere was also a bubble of magnetic control, one that shielded the planets from the harsher environment outside. The true revelations came as Voyager crossed into the Heliosheath, where the Sun's magnetic field began to clash with that of the galaxy. Here the readings became turbulent. Magnetic lines twisted, bent and folded, creating a chaotic boundary where the solar wind slowed and piled up against the pressure of interstellar space. Voyager's magnetometers captured the shifting orientation of the fields, showing how they were compressed and distorted, as though the Sun's protective bubble were being squeezed from the outside. These data helped scientists understand why cosmic rays were partially blocked from entering the solar system. The magnetic fields acted like filters, deflecting or scattering the particles before they could reach the inner planets. Without the heliosphere's magnetic shield, Earth would be far more exposed to radiation from the galaxy. Voyager's readings revealed the scale of this invisible armor, showing how far it extended and where its edges began to crumble. By studying the boundary regions, scientists gained a clearer view of how our solar system interacts with the galaxy and why life on Earth has been sheltered for billions of years. When Voyager finally reached the point where the Sun's magnetic field gave way to the galaxy's, the instruments showed that the local interstellar magnetic field was not aligned with the solar one. It was tilted, pointing in a different direction altogether. This suggested that the heliosphere was a distorted shape, squashed and stretched by the galactic field pressing against it. By tracing the direction and strength of the interstellar magnetic field, Voyager provided one of the first direct glimpses into the larger magnetic structure of the Milky Way. These measurements suggested that the galaxy is threaded with magnetic lines stretching for light years, influencing how gas clouds collapse to form stars and how cosmic rays move through space. In effect, Voyager had begun mapping not just the edge of the solar system, but the scaffolding of the galaxy beyond. The spacecraft, no bigger than a small car, had traveled so far that it was now feeling the touch of forces born in stellar nurseries and supernova remnants. Its magnetometer was like a hand stretched into the dark, brushing against threads that linked our solar system to the wider galaxy. Humanity had begun to sense the fabric of the Milky Way directly, rather than only through distant starlight. No one could fully anticipate what the magnetic environment would look like at such distances. Some models suggested a smooth transition between solar and galactic fields. Others predicted a chaotic mixing zone. Voyager showed the truth was somewhere in between. There were smooth regions, but also sudden rotations where the magnetic field flipped direction, as if the spacecraft had crossed invisible walls. These magnetic switchbacks hinted at structures that scientists still debate today. Were they remnants of the Sun's field being dragged outward, or signatures of turbulence from the galaxy itself pressing inward? Voyager's measurements provided clues but left the mystery open, ensuring decades of research to come. The spacecraft's ability to record these details was a triumph of engineering. The magnetometer booms extended far from Voyager's main body, designed to reduce interference from the spacecraft's own systems. Decades later, those careful design choices paid off, allowing the instruments to keep functioning long past their expected lifetime. Each faint signal that reached Earth carried with it information about the unseen skeleton of space. And as the years went by, scientists watched as the data built a bridge between our star's magnetic shell and the larger currents of the galaxy. The plasma shock, first direct measurements beyond the Sun's influence. Plasma, the charged soup of particles that makes up nearly all visible matter in the universe, was the true medium of space, and yet until Voyager, humanity had never dipped an instrument into the deep plasma of the galaxy. As Voyager drifted farther from the Sun, its instruments picked up disturbances in the plasma environment. These disturbances were the telltale signatures of plasma shocks. A plasma shock is like the bow wave of a ship ploughing through water, except that instead of water, it involves charged particles and magnetic fields. When fast-moving plasma slams into slower plasma, or when waves of energy race through space, a shock front is formed. For scientists, finding these shocks was like finding border markers. They revealed where one region of space ended and another began, giving a map not of land and sea, but of invisible particle flows. Voyager first encountered these shocks within the Heliosheath. There, the spacecraft detected abrupt changes in particle speed and density. It was evidence that the solar wind, once supersonic, had lost its strength and transitioned into a subsonic flow. The solar system, it turned out, had a shoreline. The Sun constantly releases coronal mass ejections, huge eruptions of plasma and magnetic energy that race outward through the solar system. On Earth, these events can spark auroras and disrupt satellites, but in the outer reaches of the heliosphere, they take on a new role. Voyager's plasma instruments recorded the shocks from these ejections as they traveled outward, slowing and spreading until they reached the frontier. These traveling shock waves carried the Sun's influence billions of kilometers from its surface, proving that even in the farthest regions of space, the Sun still spoke in bursts of energy. When Voyager finally pushed through to the boundary where the solar wind gave way to interstellar plasma, the shocks it detected became even more important. One of the most remarkable findings was the density of this interstellar plasma. The data revealed that the plasma beyond the heliosphere was denser than expected. The local galactic environment contained a measurable richness of charged particles. Voyager's instruments also recorded how shocks behaved when they crossed this boundary. As solar storms launched plasma waves outward, those waves eventually reached the interstellar medium, where Voyager could detect them as faint oscillations in plasma density. In effect, the spacecraft became a kind of cosmic seismograph, listening to the echoes of solar eruptions as they traveled into galactic space. This allowed scientists to measure not only the Sun's ongoing influence, but also the responsiveness of the interstellar medium. The ability to measure these plasma shifts was no accident. Voyager's designers had equipped the spacecraft with plasma detectors. not knowing exactly what they would find, but understanding that the behavior of charged particles would hold the key to many mysteries. These detectors, sensitive to changes in particle energy and density, became the eyes and ears of the mission in a realm where cameras could see nothing. The significance of these measurements cannot be overstated. Plasma is the dominant state of matter in the universe. Stars are made of plasma, as are nebulae, jets from black holes, and much of the interstellar medium. Yet, until Voyager, no spacecraft had directly touched the plasma of interstellar space. Its readings gave astrophysicists a baseline for understanding conditions beyond our Sun, a foundation upon which new theories could be built. In laboratories on Earth, plasma can be studied in confined experiments, but the Voyager measurements offered something no lab could: the scale and reality of plasma currents that extend for light years. When solar plasma waves hit the interstellar medium, Voyager showed that they didn't vanish instantly. Instead, they reverberated, sending ripples back and forth like vibrations in a drumhead. For scientists, this opened new questions about how the heliosphere evolves over time, and whether its shape and boundaries shift as the Sun moves through different regions of the galaxy. The sound of interstellar space, listening to plasma oscillations across the void. When Voyager 1 crossed into interstellar space, its instruments picked up plasma oscillations. The signals were steady and smooth, as though the galaxy itself was humming softly in the background. Scientists quickly realized this was more than a novelty. By studying the frequencies of these oscillations, they could determine the density of the plasma surrounding the spacecraft. The sound was not just eerie, it was data, a coded message from the interstellar medium itself. Each hum and vibration carried information about the conditions in the galactic neighborhood. The recordings became something of a cultural artifact, shared with the public. To hear them is to experience something uncanny. There is no rhythm, no melody in the human sense, only a continuous wavering tone that rises and falls as though a vast instrument is being played by invisible hands. Some likened it to the sound of a distant choir, others to the drone of wind across an alien landscape. It brought the cosmos into the realm of sensation, something we could not only study but feel. Behind the poetry of it, though, lay hard science. Plasma waves behave according to the laws of physics, responding to the density, temperature, and motion of the particles around them. By converting these waves into sound, scientists could effectively listen to the structure of space. When Voyager detected higher-pitched plasma oscillations, it meant the spacecraft was moving through denser regions. Lower tones suggested thinner gas. Over time, the recordings showed variations that hinted at turbulence, shocks, and even echoes of solar activity propagating outward across light years. This gave researchers an unprecedented way to map the invisible properties of interstellar space. Before Voyager, the interstellar medium was little more than theory. Now it had a voice. Every oscillation Voyager recorded became part of a long-term dataset, helping researchers understand how particles flow through this cosmic borderland. For the public, however, the recordings transcended pure science. They carried an almost philosophical weight. To hear the vibrations of interstellar plasma was to sense, in a deeply visceral way, our place within something larger. The thin hum Voyager captured seemed to underscore the fragility of our little world, the fact that Earth is surrounded not by silence, but by the ceaseless energy of the cosmos. It was humbling and awe-inspiring in equal measure. The plasma wave instrument responsible for these recordings was not even designed with sound in mind. Its job was to measure electrical signals in space, but when the data was shifted into audible ranges, it opened a door no one expected. Suddenly, the galaxy wasn't just numbers on a chart. It could be heard in a strange and ghostly fashion. This transformation of raw data into sensation gave Voyager's mission a human dimension, allowing people everywhere to share in the discovery. The recordings were played in classrooms, in documentaries, in art installations. Musicians sampled them, weaving the hum of interstellar space into human music. It was a reminder that science can inspire creativity, bridging the gap between knowledge and imagination. Voyager's instruments captured variations over time, almost like shifting notes. Bursts of solar activity that occurred years earlier on Earth could eventually be detected by Voyager as disturbances in the interstellar hum. It meant that the spacecraft was not isolated, but still faintly connected to the Sun, riding on echoes that stretched across billions of kilometers. As Voyager continues deeper into interstellar space, the plasma oscillations it detects remain one of the few living signs of its journey. With other instruments slowly shutting down to conserve power, the plasma wave instrument still whispers back to Earth, carrying the song of the galaxy. Each faint transmission, taking nearly a full day to arrive, is like a musical postcard from the frontier. The fact that we can still hear these sounds across such unimaginable distances is itself a marvel of engineering and persistence. In a way, the recordings form a kind of mirror to the golden record carried aboard each Voyager. One record is humanity's voice, a message of who we are and where we come from. The other is the galaxy's voice, a sound that speaks not of culture or civilization, but of the raw physics of the universe. Together, they create a dialogue across the void, human-made sound meeting natural sound. It is unlikely any alien ears will ever hear both, but for us, the juxtaposition is profound. The faint signal, how Earth still talks to spacecraft 15 billion miles away. From the surface of Earth, Voyager is now more than 15 billion miles away. At that range, the spacecraft has become little more than a speck, drifting in the endless ocean of interstellar space. And yet, somehow, we still talk to it. Across this gulf, the spacecraft continues to whisper home. Its voice is not loud or clear. It is fragile, stretched thin by distance, and weakened to the edge of nothingness. The signal that arrives at Earth is billions of times weaker than the static hiss of a television left untuned. And yet, it is unmistakably there. That faint pulse of radio energy, almost vanishing into the background of the universe, is the connection between us and the most distant emissary we have ever launched. Voyager's transmitter sends signals using about the same wattage as a refrigerator light bulb. At the beginning of its journey, this was more than enough. From the vicinity of Jupiter or Saturn, the signals were strong and clean, even with modest receiving dishes on Earth. But as the spacecraft pressed outward, that same transmission had to stretch farther and farther. Imagine a flashlight beam spreading wider the further it travels, growing dimmer until it is almost invisible. That is what Voyager's radio signal has become. After 15 billion miles, the beam has expanded so much that only a vanishing fraction of its power ever reaches Earth. What remains is a whisper buried in cosmic static, a message that requires enormous effort to extract. On Earth, we catch these signals using the Deep Space Network, or DSN, a collection of giant radio antennas located in California, Spain, and Australia. Each dish is vast, some stretching 70 meters across, built with exquisite precision so they can collect even the faintest trickle of photons arriving from deep space. These antennas are among the most sensitive ears ever created by human hands, capable of picking up Voyager's signal, even though it is weaker than the noise of the sun and drowned out by the hiss of the galaxy. The task is something like hearing the crackle of a match in the middle of a hurricane. Yet, by carefully filtering and amplifying the signals, scientists and engineers can reconstruct Voyager's transmissions with remarkable accuracy. The time delay itself adds to the strangeness of the connection. A message sent from Voyager takes more than 20 hours to reach Earth, traveling at the speed of light. When engineers issue a command from Earth, they must wait almost 2 days before seeing the spacecraft's response. This means that communication is not a conversation, but a long, slow exchange. Each instruction, each confirmation, each piece of data crawls across the void, a patient dialogue stretched across billions of miles. The spacecraft itself must carry out tasks largely on its own, relying on pre-programmed sequences, because there is no way to guide it in real time. The fragility of this communication cannot be overstated. Voyager's hardware is old. its systems primitive by modern standards. Its computer memory is measured in kilobytes and was never designed to last this long. The radio link has endured decades of storms, flares, and interference, yet remains unbroken. It is a triumph of both design and perseverance, proof of what careful engineering can accomplish. Each day, engineers schedule time on the DSN to listen for Voyager's voice. They wait for the faint signal to arrive, checking it for signs of weakness, interpreting its coded information. This has been happening for more than 4 decades. The fact that we can still listen at all is remarkable, but even more so is the decision to keep listening. We could have let Voyager drift into silence long ago, forgotten in the immensity of space. Instead, we continue to reach out, unwilling to let go of the fragile thread that binds us to it. To visualize just how faint Voyager's signal is, consider this. By the time it reaches Earth, its power has diminished to less than a billionth of a watt. It is so weak that without the giant antennas of the DSN, it would be completely undetectable. And yet, because the signal is so stable and predictable, engineers can sift it out of the background noise. By averaging over long periods of time and locking onto its frequency, they can recover data from what would otherwise be lost. This process is not unlike finding a single grain of sand on a vast beach, except the beach stretches across light years of space. Voyager still returns measurements of the environment it moves through, the density of plasma, the strength of magnetic fields, the levels of cosmic rays. Every bit of information must be compressed and transmitted with utmost efficiency because the data rate is painfully slow. At this distance, Voyager can only send back information at a few hundred bits per second, slower than the speed of a 1980s dial-up modem. And yet, within those slow streams are insights no other spacecraft has ever provided. Each byte of data is precious, hard-won, and historic. When a photon leaves Voyager's antenna, it travels through interplanetary space, past the orbit of Neptune, beyond the heliosphere, across billions of kilometers of emptiness, before striking the surface of a dish on Earth. That single photon may be the survivor of an unimaginably long journey, carrying with it a trace of information encoded decades earlier by a machine built by human hands. To capture that photon, decode it and understand its meaning is to participate in an act that binds our world to the stars. We know that one day the spacecraft's power will fade. The plutonium in its generator is slowly decaying. Instruments have already been switched off to conserve what little remains. In time, even the radio will fall silent. When that happens, the faint thread that has connected us to Voyager for nearly half a century will break, and Earth will no longer hear its voice. The spacecraft will continue on, but without communication, it will become just another silent wanderer in the dark. Until that day, however, we continue to listen. Each time the DSN locks onto Voyager's signal, humanity proves its persistence. We insist on hearing the voice of our emissary, no matter how faint. It speaks to our desire to remain connected with the things we send into the void. The signal tells us that Voyager is still there, still alive in some sense, still bridging the unfathomable distance between us and the frontier of the galaxy. Ancient computers in the future, how outdated tech still guides a pioneer. Voyager carries 3 onboard computers, each dedicated to specific tasks. The command and control subsystem handles instructions sent from Earth, interpreting the carefully coded signals and turning them into actions. The flight data subsystem manages the flow of information from Voyager's instruments, packaging data and sending it home. And the attitude and articulation control subsystem is responsible for keeping the spacecraft properly oriented, ensuring its antenna stays pointed at Earth and its instruments at their targets. Together, these computers form a system that is less powerful than the processor inside a basic calculator today. Each one has just a few kilobytes of memory, an amount so small that it can be difficult to grasp in an age where a single photograph on a phone requires thousands of times more storage. The limitations of these computers meant that Voyager could not make decisions on its own in the way modern spacecraft sometimes can. Instead, it relies on long, carefully written command sequences uploaded from Earth. Teams of engineers had to design and test every set of instructions, often weeks in advance, before sending them across billions of miles of space. Once received, Voyager would slowly work through them, step by step, without improvisation. The spacecraft does not think, it executes. This simplicity has meant fewer opportunities for unforeseen glitches, fewer layers of software to fail, and less reliance on delicate, miniaturized parts that might not have survived the extremes of deep space. In the 1970s, the very idea of programming a spacecraft to function autonomously for decades was unprecedented. Memory was scarce, processing power was limited, and every line of code had to be written with extraordinary efficiency. The engineers were forced to think with precision, stripping away anything unnecessary, designing routines that did exactly what was needed and nothing more. In doing so, they created systems that could run reliably, without the burden of complexity that plagues modern software. What seems primitive now was, in fact, elegant in its clarity. Voyager's outdated technology has another advantage. It was built in an era when computers and circuits were larger, slower, and often more robust against radiation and electrical disturbances. The spacecraft has traveled through regions saturated with powerful magnetic fields, harsh cosmic rays, and bursts of charged particles from the Sun. In theory, these conditions could scramble or destroy a modern microchip. Voyager's bulkier, less delicate electronics have proven unexpectedly hardy, shrugging off radiation that might cripple a thinner, faster circuit. What was once seen as a limitation has become a shield. But durability does not mean the system is free from challenges. Operating computers this old requires constant adaptation on Earth. The engineers who first built Voyager have long since retired, and many of the technologies they used have vanished from everyday use. To keep the spacecraft running, modern teams have had to relearn, recreate, and sometimes reinvent the knowledge of the 1970s. Old manuals are pulled from archives. Original design notes are studied, and in some cases, engineers build replicas of Voyager's hardware on Earth just to test new instructions before sending them into space. Communicating with Voyager today is like speaking a dead language, one that must be mastered anew by each generation of caretakers. The spacecraft's limited memory and processing power also force difficult choices. Not all instruments can be run at once, and not all data can be sent home. Every byte of information must be planned, prioritized, and filtered. Commands must be short and exact, often requiring creative workarounds to make the most of the available capacity. Where a modern probe might beam back torrents of high-resolution images and measurements, Voyager can only send its findings slowly, piece by piece, like a trickle of water dripping from a faucet. Voyager's computers are machines from another era, built at a time when the internet did not exist, when personal computers were rare curiosities. And yet, some of the oldest computers we still operate are also the most futuristic, carrying out tasks that no other machine has ever attempted. In a world where devices are replaced every few years, Voyager reminds us that longevity can matter more than speed, that reliability can matter more than innovation. It suggests that the best machines are not always the most advanced, but the ones that can be trusted to endure. The spacecraft's survival is not a story of cutting-edge power, but of careful design, simplicity, and patience. Course corrections in the dark, keeping Voyager steady with limited tools. Unlike a ship with sails or a plane with wings, Voyager depends entirely on the slow push of thrusters, bursts of gas smaller than the puff of air from a human breath. Each one is deliberate, chosen after days of planning, calculated to nudge the spacecraft just enough to keep its antenna pointing home. Without these adjustments, its voice would fade into the void, unable to reach Earth. The difficulty is that these thrusters are not infinite. Half a century later, their age is showing. The challenge is no longer simply to guide the spacecraft, but to do so with the most fragile tools imaginable. NASA engineers must think in terms of scarcity. The fuel that feeds the thrusters, hydrazine, cannot be replaced. Once it is gone, no maneuver will ever be possible again. The decision to fire the thrusters is no longer routine, but weighed like a doctor prescribing the last of a precious medicine. Each pulse costs fuel, and each gram of fuel carries Voyager closer to the day when it can no longer answer Earth's call. That makes every course correction an act of restraint, balancing necessity against preservation. The engineers who command Voyager must constantly ask themselves, is this adjustment truly worth the price? Orientation is everything. The spacecraft's large high-gain antenna must remain fixed on Earth. If it drifts even a small fraction of a degree, its signal can weaken or vanish. The DSN is powerful, but even it cannot pick up a voice that isn't speaking directly toward it. That makes pointing the antenna Voyager's single most important task. To achieve this, engineers use star trackers and gyroscopes, instruments that measure the spacecraft's position against the background of the universe. Yet with age, many of these systems have degraded. What remains must be used sparingly, checked against long-range calculations and corrected when drift sets in. Sometimes the solution has been to switch to thrusters that had not been used in decades. In 2017, NASA made the decision to test a set of backup thrusters on Voyager 1, which had been dormant since the flyby of Saturn in 1980. Against all expectations, they worked. After nearly 4 decades of silence, the small devices fired once again, as if waking from a deep sleep. It was a remarkable moment, a reminder that the spacecraft still had hidden reserves of resilience. But even this was temporary relief. Old thrusters are still old thrusters, and fuel remains finite. The wear and tear of time reveals itself in subtle ways. Tiny leaks can develop in fuel lines. Valves can stick. Firing patterns that once worked smoothly must now be altered to account for sluggish response. The engineers on Earth adapt, rewriting code and creating new sequences to coax the spacecraft into cooperation. They do this with hardware so old that some of the people who designed it have long since passed away. Manuals and blueprints are dug out of archives, sometimes written by hand or typed on yellowed paper. A burn lasting less than a second might consume fuel measured in grams, yet those grams could mean weeks, months, or even years of extra life. Each correction buys more time, keeps the antenna steady, and allows the faint signal to continue its journey home. The spacecraft is measuring regions of space no probe has ever entered before. Losing it would mean losing our only direct witness to this frontier. It is easy to imagine course corrections as dramatic, like rockets blazing across the sky, but in reality, they are almost imperceptible. Voyager continues on its trajectory at tens of thousands of miles per hour, while the thrusters make only the smallest changes to its angle. It is like turning a great ship with the gentlest flick of the rudder. Yet these small adjustments matter enormously. Without them, Voyager's antenna would slowly drift until Earth was out of view, leaving the spacecraft shouting into the void with no one to hear. The patience required for this work cannot be overstated. An engineer sends a command, waits 20 hours for the signal to reach Voyager, and then another 20 for the response to return. If something goes wrong, the cycle repeats, stretching days into weeks for even the simplest troubleshooting. This means that course corrections are not just technical operations, but exercises in endurance. They test not only the spacecraft, but the humans guiding it. As Voyager drifts further, the challenges will only increase. Its fuel will dwindle, its thrusters will weaken, and the delay in communication will stretch longer. Eventually, there will be a final correction, the last adjustment made before the spacecraft can no longer respond. But until that moment arrives, engineers continue to calculate, to plan, and to trust their craft. Each time Voyager steadies itself in the dark, it is a triumph of persistence over distance, of human patience over the silence of space. Voyager's lessons for Cassini, New Horizons, and beyond. Cassini, Galileo, and New Horizons were built with Voyager's successes and surprises in mind, designed to refine what Voyager had glimpsed and to probe deeper into the mysteries it had uncovered. In this way, Voyager was not only an explorer but a teacher, and its lessons continue to ripple across decades of spaceflight. Jupiter was the first proving ground. Before Voyager, Pioneer 10 and 11 had flown by, giving humanity its first close looks, but they lacked the sophistication to capture the full complexity of the gas giant system. Voyager's dual flybys of Jupiter in 1979 changed everything, and those discoveries forced scientists to think bigger about what the giant planet's moons could be. Engineers designed Galileo with instruments capable of probing beneath Europa's ice, and with cameras prepared to catch volcanic activity on Io in real time. Galileo was, in many ways, Voyager's direct descendant, sent back to a world whose complexity had been revealed only because Voyager had dared to take a closer look. Saturn offered another chapter of influence. Voyager's encounters in the early 1980s gave humanity its first detailed images of the planet's rings, showing them not as uniform bands. The missions also discovered new moons and revealed Saturn's atmosphere as more dynamic than previously imagined. When Cassini was conceived in the 1990s, its entire mission plan was built on filling the gaps that Voyager had uncovered. Cassini carried instruments tuned to study the structure of the rings in detail, to map Saturn's magnetosphere, and to land a probe, Huygens, on Triton, whose thick atmosphere Voyager had only hinted at. The images of Titan's hazy orange shroud from Voyager made it clear that here was a world with mysteries too big to ignore. Cassini was, in many ways, Voyager's promise fulfilled, delivering what a short flyby never could: long-term presence and patient study. Voyager's trailblazing also reached further, beyond the gas giants, and into the frozen edge of the solar system. For decades, Pluto had been little more than a blurry speck through telescopes. Voyager did not visit it. It was already headed in another direction after Saturn, but its pathfinding laid the groundwork for New Horizons, which launched in 2006. Voyager proved that a spacecraft, if designed with patience and foresight, could endure for decades and travel distances once thought unreachable. This emboldened planners to design New Horizons as a mission not just to Pluto, but to the Kuiper Belt beyond, knowing that the precedent had already been set. Voyager showed that the outer solar system was within reach of human technology, and that even fragile instruments could survive the cold, the distance, and the long silence of travel. The technical lessons were just as important as the scientific ones. Voyager demonstrated the value of gravity assists. Without Voyager's successful use of this maneuver, later missions might have been impossible or prohibitively expensive. New Horizons relied on a Jupiter flyby to reach Pluto in time for its 2015 encounter, shaving years off its journey. Cassini, too, made use of multiple assists, including Earth and Venus, to gather enough speed to enter Saturn's orbit. The very architecture of deep space travel owes its success to the validation Voyager provided. Voyager also taught engineers how to prepare for the unknown. Many of the instruments on board were designed to be flexible, capable of detecting not only expected phenomena, but also surprises. This adaptability paid off when volcanic activity was discovered on Io, or when the structure of Saturn's rings proved more complex than anyone imagined. Later missions adopted this same mindset. Galileo carried instruments capable of detecting magnetic signatures that could hint at subsurface oceans, while Cassini's suite of sensors was designed with a wide enough scope to explore everything from Titan's lakes to the geysers of Enceladus. The philosophy was simple: expect the unexpected, because Voyager had shown that the universe rarely fits within neat boundaries. The endurance of Voyager also inspired a shift in how missions were envisioned. This longevity encouraged NASA and other space agencies to think long-term, designing missions that could adapt as circumstances changed. Cassini, originally planned for a 4-year primary mission, was extended multiple times, lasting over 13 years in orbit around Saturn. New Horizons 2 was extended beyond Pluto to study Kuiper Belt objects, with plans to keep it alive as long as possible. Voyager's story had shown that missions did not need to end when their primary objectives were completed. With creativity, they could evolve into something new. Another lesson lay in communication. The faint signals from Voyager pushed the limits of the DSN, forcing upgrades to the giant antennas on Earth and refining the techniques used to pull faint whispers from the cosmic noise. These upgrades were not for Voyager alone. They benefited all missions that followed. By the time New Horizons reached Pluto, the ability to receive data from billions of miles away with clarity had become a normal part of deep space exploration. But it was Voyager that first demanded those capabilities. The infrastructure Voyager required became the foundation for future missions' success. Even culturally, Voyager set a precedent. Its golden record, carrying sounds and images of Earth as a message to the stars, embodied a spirit of outreach that inspired later efforts to connect missions with the public. Cassini carried no record, but its final plunge into Saturn was framed as a dramatic grand finale, a story told to millions worldwide in real time. New Horizons' flyby of Pluto was celebrated globally, with people gathering in public spaces to watch images arrive from the edge of the solar system. Voyager had shown that exploration was not just for scientists, but for all humanity. Later missions carried that torch, treating their discoveries as shared moments for the entire species. The bridge between Voyager and the missions that followed is clear in every image, every dataset, every trajectory that was chosen. Without Voyager, Galileo might not have known where to look on Europa. Without Voyager, Cassini might not have been designed to probe Titan's atmosphere or Enceladus's geysers. Without Voyager, New Horizons might never have had the confidence to aim for Pluto and beyond. Each of these missions was an extension of Voyager's vision, a continuation of the first great leap outward. From Voyager to interstellar probes, the blueprint for future journeys. Voyager has traveled for decades and has only just entered the interstellar medium, a place still very close to home when compared with the vastness of the galaxy. At its current speed, it would take tens of thousands of years to reach the nearest star. For future probes, engineers dream of faster propulsion methods that could bring those timescales down to centuries or even decades. Concepts like nuclear pulse propulsion, where a spacecraft rides the controlled explosions of atomic charges, or fusion engines that harness star-like reactions, are serious proposals on the drawing boards of visionary scientists. Voyager's journey has forced us to realize that speed is not a luxury in interstellar exploration, it is a necessity. Without it, the stars remain forever out of reach. Voyager carries heavy instruments, built in an era when every sensor required substantial space and power. Today, engineers imagine fleets of tiny probes, each no larger than a smartphone, riding on sails powered by lasers from Earth. Projects like Breakthrough Starshot take direct inspiration from Voyager's crossing, asking how we could shrink an interstellar mission to the smallest possible form and accelerate it to a significant fraction of light speed. Instead of a single massive craft venturing into the galaxy, we could send thousands, each carrying cameras, sensors, and transmitters. Voyager showed that one probe could open the way. The future may see swarms of them, scattering like seeds into the interstellar wind. For future probes, engineers will need to rethink how data flows across such distances. More powerful transmitters, larger antennas, or even entirely new methods, such as laser communication, may define interstellar missions to come. Voyager's faint whispers remind us that while we can hear across the void, future probes must speak louder and more clearly if they are to deliver meaningful streams of information from across the stars. Voyager was designed for planetary exploration, and its entry into interstellar space was, in many ways, a bonus. Future interstellar probes will not stumble into the galaxy, they will be launched for it. Their instruments will be chosen to study the local interstellar medium, to measure cosmic rays, to map magnetic fields, and perhaps even to scan for signs of nearby planets or stars. They will not just be emissaries of Earth, but scouts of the galaxy. Voyager has shown that the space beyond the heliosphere is alive. Future probes will be designed to listen, to map and to chart these unseen landscapes with precision. There are already proposals in the works that embody these blueprints. One concept, known as the Interstellar Probe, is being studied as a possible NASA mission for the coming decades. Unlike Voyager, it would not be an accidental traveler, but a deliberate one, built to cross the heliopause and dive deeper into the interstellar medium. It could travel at twice or 3 times Voyager's speed, mapping the boundary where our Sun's influence ends and the galaxy begins. Its instruments would measure the interstellar wind, the magnetic fields, and the distribution of cosmic dust, providing data no human instrument has yet collected. Voyager has shown us the doorway exists. The interstellar probe could be the first to truly walk through it. The dream extends further still. Imagine a probe designed not just to leave the solar system, but to reach another star within a human lifetime. Such missions are still speculative, relying on technologies that do not yet exist. But the blueprint is there, written by Voyager's endurance, its faint signals and its golden message. To chase that dream is to expand what Voyager began, to transform the idea of interstellar space from a distant concept into a reachable frontier. Voyager is not the end of the story, but the first page. Future interstellar probes will be faster, smarter, and stronger. They will carry instruments tuned for the galaxy itself. They will be designed not for decades, but for centuries. And yet, no matter how advanced they are, they will trace their lineage back to a pair of spacecraft launched in the 1970s, built with ancient computers and powered by decaying plutonium. Could humanity ever visit Voyager again? The physics of chasing our own probes. Voyager 1, the most distant object ever built by human hands, is now more than 25 billion kilometers from Earth as of September 2025. It races through interstellar space at a speed of about 61,000 kilometers per hour relative to the Sun. At such distances and velocities, the spacecraft has long passed beyond the reach of routine missions. Nothing humanity has launched since has come close to overtaking it. This fact creates a peculiar situation. Though Voyager belongs to us, though it is our artifact, our emissary and our messenger, it is in every practical sense out of reach. To think of ever visiting it again is to imagine not just a technical challenge, but a philosophical one. It is to imagine whether we could, someday, chase down a piece of our own past, not for resources or survival, but for memory. The physics of this pursuit are daunting. To catch Voyager, a spacecraft must do more than simply reach interstellar space. It must surpass Voyager's speed, accelerating for years or decades until it overtakes the probe. The energy requirements are staggering. For chemical rockets, the workhorses of the space age, such a mission is effectively impossible. Their efficiency, while good enough to lift astronauts to the Moon or probes to Mars, cannot provide the sustained acceleration required to close the gap. Even our fastest missions, like New Horizons, which flew past Pluto, remain slower than Voyager. New Horizons left Earth with incredible speed, yet Voyager, with its planetary gravity assists, continues to lead the race into interstellar space. If we wanted to plan a chase today, we would need to think differently about propulsion. Solar sails offer one intriguing pathway. By using the pressure of sunlight on a large reflective surface, a spacecraft could accelerate slowly but continuously, gaining speed over long distances. A solar sail launched close to the Sun could achieve tremendous velocities, perhaps even overtaking Voyager after decades. But even this method faces limits. Voyager has already traveled too far for sunlight to be an effective driver. Once in interstellar space, the photons are too faint. Unless a sail were paired with a powerful ground-based or orbital laser array, it would lose its push in the dark between stars. Nuclear propulsion presents another possibility. Concepts like nuclear thermal rockets or nuclear electric propulsion could provide sustained thrust far beyond chemical fuels. These designs remain on the drawing board, tested only in parts, never in a full interstellar chase. More radical still are ideas like fusion drives, which could harness the power of the same reactions that fuel stars. If humanity ever builds a working fusion engine, it might be possible not only to send ships to Voyager, but to do so within a human lifetime. Imagine a craft accelerating steadily across the solar system, leaving behind the outer planets and finally reaching the faint signal of Voyager after only a few decades. Antimatter propulsion, still deeply theoretical, would make the chase trivial by comparison. With efficiencies thousands of times greater than chemical rockets, antimatter drives could accelerate ships to fractions of the speed of light. Such technology could allow humanity to overtake Voyager in years rather than centuries. But this is no more than speculation for now. We do not yet know how to produce, store, or use antimatter in practical quantities. To speak of visiting Voyager with such technology is to speak not of engineering, but of the dreams of a far future. Still, the thought experiment carries weight. A future civilization capable of reaching it would almost certainly have surpassed the limitations that once held us earthbound. To them, Voyager would not be a technological marvel, but an antique. Its golden record, its tape-recorded data systems, its crude computer memory, all would be laughably primitive compared to their own tools. Yet that very primitiveness is what makes Voyager precious. It is not a treasure of technology, but of heritage. To hold Voyager again would be to hold proof of our first leap into the unknown, an object that once carried our curiosity beyond the cradle of our solar system. In practical terms, a mission to reclaim Voyager would not be efficient. The probe has no scientific value compared to what more advanced instruments could provide. Its instruments are failing, its power is dwindling, its signal grows weaker by the day. Any mission designed purely for science would bypass Voyager and press deeper into the galaxy. And yet, the idea of reaching it again holds a strange pull. It would be like visiting a monument, not for discovery, but for remembrance. Future astronauts or robotic explorers might approach Voyager not with the excitement of new data, but with the reverence of archaeologists uncovering a lost artifact. Imagine that scene. A sleek interstellar craft, built centuries after Voyager's launch, slowing as it approaches the small, aging probe. The golden record glints faintly in the starlight. Its once polished surface, weathered by cosmic dust, still clings to its message. To future humans, the act of docking with Voyager would feel like touching the hands of their ancestors across the gulf of time. Perhaps they would bring it aboard, placing it in a museum of interstellar exploration. Perhaps they would leave it drifting, choosing instead to honor its solitude, only brushing past as a sign of respect. The question then becomes less about physics and more about values. Would future humanity, capable of sending ships across light years, care enough to chase down an ancient probe? Or would it be too busy with larger pursuits? Colonies, new worlds, communication with other species? In a future of endless horizons, Voyager might be too small to matter. Yet there is also the chance that its symbolism would grow precisely because of its smallness. In a universe of incomprehensible scales, Voyager is the thread that ties us back to our beginnings. A future civilization might see value in reuniting with it. Even today, some argue that if humanity ever builds a probe with faster-than-light travel or near-light propulsion, Voyager would be the first destination we should revisit. Not because it will teach us anything new about physics or biology, but because it reminds us of who we were. In that sense, the journey to catch Voyager would be a pilgrimage rather than an expedition. It would show that even in the age of stars, we still care about the fragile messages we once carved into metal and sent drifting into the void. Perhaps the most poetic possibility is that we never reclaim Voyager, that it remains forever out there, untouchable, an eternal traveler. Yet even then, the dream of chasing it carries weight. For in thinking about whether we could catch Voyager, we are forced to imagine technologies beyond our reach, futures beyond our present. Voyager, still traveling outward, continues to push our imagination forward. It may be physically out of reach, but as long as we think of going after it, it still guides us, still shapes the story of human curiosity. Voyager has left us a strange paradox. It is ours, yet it no longer belongs to us. It is beyond reach, yet never beyond thought. To wonder whether we could ever visit it again is not simply to ask a question about rockets and propulsion. It is to ask whether we will ever care enough to look back at our own history, drifting alone in the stars, waiting for us to catch up. The golden record in context, what we chose to say to the cosmos. When people think of the Voyager missions, perhaps the most enduring part of the mission is not the instruments or even the discoveries, but a small phonograph record bolted to the side of each spacecraft. It is called the Golden Record, and unlike the sensors that measure magnetic fields or the cameras that once captured alien landscapes, its purpose is not scientific. It is cultural, symbolic, and deeply human. If the spacecraft are messengers of science, the record is a message of spirit, a portrait of who we are. The idea of including a message began with earlier missions. Pioneer 10 and 11 carried small plaques designed by Carl Sagan and Frank Drake that depicted the location of our solar system, the outline of the spacecraft, and a pair of human figures. These were simple greetings, postcards in a sense, offered to anyone who might encounter them in the distant future. The Voyager Golden Record, however, was a phonograph disc made of copper plated in gold, containing sounds, music, and images. It could be played, at least in theory, by any being that found it, provided they could decipher the instructions etched into its casing. The creation of the Golden Record was not a casual effort. A team led by Carl Sagan, with the help of writers, artists, and scientists, worked to decide what exactly should be included. They had to wrestle with difficult questions. What does it mean to represent humanity? How do you distill an entire species, an entire planet, into a small package that might be discovered millions or billions of years from now? What images, sounds, and words could capture the richness of Earth without overwhelming or confusing an unknown audience? The team worked on a tight schedule, racing to complete the content before the spacecraft launched in 1977. Every decision carried weight, and every inclusion or omission was debated. The record ultimately carried 115 images, encoded in analog form, depicting scenes from Earth. These ranged from simple scientific diagrams, like the structure of DNA, mathematical equations, and the solar system, to photographs of human life. There were pictures of people eating, working, laughing, and learning. There were images of landscapes, mountains, rivers, deserts, and oceans. There were animals, from elephants to dolphins and plants, from wheat fields to trees. The goal was to show the diversity of life, the beauty of the planet, and the universality of human experience. The images told a story without words, one that any intelligence, human or alien, might grasp. This is a living world, and we are its curious inhabitants. Alongside the images came sounds. The record includes greetings in 55 different languages, some ancient and some modern. These greetings range from the formal to the playful, from serious invocations of peace to simple hellos. Together they form a chorus, a reminder that humanity does not speak with one voice, but with many, and that diversity is part of our identity. The record also contains the sounds of Earth itself: wind, rain, waves, birdsong, and the calls of animals. These natural noises anchor the record in the world that gave rise to us, offering a kind of acoustic fingerprint of our home. And then there is the music. Music is both deeply human and potentially universal. It follows patterns of rhythm and tone that might resonate even with beings unfamiliar with Earth. The team chose a selection of pieces from across cultures and centuries. Classical works by Bach and Beethoven were included alongside folk songs from around the world, Native American chants, and performances from countries like Japan, China, Peru, and Senegal. One of the most striking inclusions was Chuck Berry's Johnny B. Good, a piece of American rock and roll that at the time represented both modern energy and cultural boldness. Some scientists questioned whether rock music should be sent into space, but Sagan insisted that it was authentic to who we were, part of the richness of human expression. The final record thus became a kind of global mixtape. The spoken message of the record came from the United Nations Secretary General at the time, Kurt Waldheim, who offered greetings of peace on behalf of humanity. There was also a message from US President Jimmy Carter, who wrote of the record as a symbol of hope, that one day spacefaring civilizations might look upon Earth as a place where people, though divided, dreamed of reaching the stars. This layering of voices, political, cultural, natural, gave the record a sense of depth, as if it were not just a collection of artifacts, but a carefully woven narrative of humanity's place in the cosmos. Anne Druyan, a member of the team, volunteered to have her brain activity recorded as she thought about history, philosophy, and her personal experiences. Unknown to most at the time, she had just become engaged to Carl Sagan, and her thoughts of love, wonder, and excitement were encoded into the record as patterns of electrical signals. This means that, hidden among the greetings and songs, is the inner life of a single human being, captured at a moment of joy. It is perhaps the most intimate and poetic gesture of the entire project, a reminder that the record was not only about facts and figures, but about the emotions that make us human. The Golden Record is often described as a time capsule, but it is more than that. It is a statement of intent. It says that humanity, despite its conflicts and imperfections, sees itself as part of a larger universe, willing to introduce itself to the unknown. It says that we are not afraid to be heard, even if no one ever listens. For while the chance of the record being found is vanishingly small, the odds of an alien civilization stumbling upon one of the Voyagers are almost zero. The act of creating it mattered deeply to us. It forced us to reflect on ourselves, to ask what was worth sharing, and to recognize that our differences could be framed not as barriers, but as richness. From a scientific perspective, the record is not necessary for the mission. Voyager's instruments do not depend on it, nor does the data it sends back. Yet many argue that the Golden Record is the most important part of Voyager, not because of what it will achieve, but because of what it represents. Long after the spacecraft stop transmitting, long after Earth itself may have changed, the records will still exist, silent and unplayed, drifting between the stars. In them is a snapshot of humanity at a particular moment in history, a self-portrait cast into eternity. Voyager's scientific legacy may fade as instruments die and data streams cease, but the Golden Record will remain as a cultural artifact, perhaps the longest-lasting one our species will ever create. What aliens might think of our message in a bottle. If one day, long after humanity is gone, the Voyager probe drifts into the hands of an alien civilization, the encounter would be a meeting of minds across an almost unimaginable gulf of time and space. The Golden Record is a whisper across the cosmic ocean that says, "We were here." But whether that whisper would be understood, mistranslated, or ignored depends entirely on the beings who might find it. To them, it would not carry the same cultural weight as it does for us. They would see it without the backstory of Carl Sagan, NASA engineers, or Cold War tensions. For them, it would simply be an object, adrift, preserved in interstellar cold, waiting to be interpreted. The first question such a species might face is whether Voyager itself is alive or dead. To us, it is a silent machine. To them, depending on their understanding of life, it could appear as a relic of some cybernetic creature, perhaps a fossilized drone of a civilization that blurred the lines between biology and technology. The Golden Record's carefully crafted grooves might look like ribs, like the structural remains of an organism that encoded its essence not in DNA, but in vibration and metal. For a species whose own way of preserving knowledge is entirely different, perhaps in light patterns, neural spores, or electromagnetic imprints, the very idea of carving sounds into a disk might seem primitive, strange, or even incomprehensible. Yet strangeness itself might be the very clue that tells them this was made with intention. When they discover the record's cover, etched with diagrams and instructions, their minds might turn to decoding it. The pulsar map showing our location in relation to 14 nearby pulsars could either be their first point of recognition or their first moment of confusion. If they too have mapped the cosmos and understand pulsars as we do, spinning beacons of incredible regularity, then this part of the message might shine like a universal Rosetta Stone. They might trace the lines, follow the timings, and find the faint mark of a small yellow star on the outskirts of a spiral galaxy. To them, that would be the place where this strange artifact was born. But if they have never studied pulsars or interpret them not as astronomical phenomena but as something more mystical, then the etching might appear as pure geometry, devoid of meaning. What to us is a map could to them be an abstract symbol or perhaps a puzzle with no solution. Suppose they do open the record and discover its sounds and images. Their first sensation may be bewilderment, a whale song stretching across cosmic silence, the crackle of thunder, greetings in dozens of human tongues, all compressed into grooves of gold, would sound like nothing from their own world. To them, it could be noise, or it could be evidence of voices. If they themselves do not communicate with sound at all, the very idea of voice might be alien. Perhaps they communicate through shifts of color across their skin or by chemical signals carried in air or liquid. In that case, the golden record's human speech could seem like chaotic pressure waves, yet the repetition of syllables might betray a pattern, not random but structured. The word hello in English might sound to them like the drumbeat of intention, even if the meaning remained locked away. The images engraved into the record would pose an even greater challenge. The 116 pictures, when decoded through the instructions, reveal our bodies, our families, our landscapes, our DNA, our cities. Yet would aliens see what we see? Our image of two humans, a man and a woman, standing side by side, might to them appear as stick-like organisms, upright and bare. They might misinterpret the gesture of the raised hand not as a greeting, but as a threat or ritual. A photo of a bustling city could be seen as a complex nest or hive. The double helix of DNA might mean little if their own life is based on entirely different chemistry. Still, the repetition of spiral structures, the symmetry of the human face, the geometries of architecture, all of it would suggest that whoever made this record had intention, intelligence, and a way of shaping the world around them. The music might be the most universally comprehensible part. Mathematics hides inside rhythm. Ratios live in harmony. A being unfamiliar with Bach or Blind Willie Johnson might still notice the structure, the recurrence of themes, the non-random intervals. Music carries emotional tones even without shared culture. A slow, mournful melody might feel different from an energetic drumbeat. It's possible that a civilization far older than ours would recognize music as a sign not just of intelligence, but of something more elusive, a capacity for beauty, for expression beyond survival. That realization might be the true breakthrough moment, when they stop seeing Voyager as debris and begin seeing it as a voice. But there is another possibility. Aliens might not see the golden record as a message at all. To them, it could be an artifact, like pottery shards from a forgotten people. They might admire it as art, puzzling over the grooves as decorative rather than functional. In their museums, it might rest as a curiosity, the relic of an extinct species who once looked at the stars. Perhaps they would even study it not as a communication, but as a warning, a record of beings who reached into space but never followed. If they searched the skies for signs of us and find only silence, they might assume we are long gone, vanished into cosmic extinction, our only trace this fragile disk of gold. And what if the aliens are not benign? If they find our probe and are capable of reaching its place in interstellar space, then they already surpass us in technology. For them, the record might not be an invitation, but a vulnerability. The pulsar map shows exactly where we are. Would they see that as reckless, as naive, or as proof that the senders of this object were eager to be found regardless of consequence? In such a case, the golden record might spark debate among them, much as it has among us. Should they follow the trail back to its source, or leave the strange little artifact drifting, respecting the distance between civilizations? Voyager was designed for us. The golden record is less a message to the stars than a reflection of who we were at a particular moment in time. If aliens ever find it, they will not be decoding humanity as it exists in their present. They will be decoding a memory, a fossilized self-portrait from the late 20th century. The music they hear will not be the music of the future, the images not the cities we have yet to build, the greetings not the languages that may evolve over centuries. Instead, they will see a frozen version of us, one that may no longer exist by the time they hold the record in their hands. To them, we might appear extinct even if we survive. To them, the record is evidence of what was, not what is. Perhaps that is why the golden record is so moving, not because it promises contact, but because it guarantees memory. Somewhere, someday, someone may know that humanity once looked outward, once cared enough to carve its existence into gold and set it free. Whether they laugh at its simplicity, marvel at its beauty, or misunderstand its meaning entirely, the record will still have done its work. It will have carried our voice further than any of us could. How do you think they would react? And what topic would you like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.